Hello again, and welcome back to this quiet corner where curiosity slows down and science takes its time. Tonight we are asking a question that sounds simple but is anything but. When physicists talk about nothing, what do they actually mean? And more provocatively, could the Big Bang, the origin of everything we see, have actually emerged from nothing? At first glance, it might sound straightforward. Nothing should mean empty space. No matter. No stars, no galaxies, no air, no atoms, just emptiness. But the deeper you go, the less clear that picture becomes. Physics has a way of turning what seems obvious into something far stranger than we first imagined. Before we begin this journey into the nature of nothingness and existence, I would love to know where you are right now. What time is it in your part of the world? Are you settling in for the night? Or perhaps it is already deep into the quiet hours. Maybe you are somewhere in between, in that suspended moment when the day has released you and sleep is beginning to call. It brings me comfort to imagine that across all the time zones, across continents and oceans, people are gathering in this same contemplative space, each preparing to let go of the day's concerns and drift into something larger. Something that touches on the most fundamental questions we can ask. If you find value in these explorations, a like or subscribe helps this channel continue to grow, helps these gentle investigations reach others who might benefit from a calm voice and vast perspective as they move toward rest. For those already part of this community, thank you. You are part of this voyage into understanding. Tonight's question is ancient. Philosophers have asked it for millennia. Why is there something rather than nothing? But what makes our exploration different is that we are approaching it through physics, through the actual discoveries and theories that scientists have developed over the past century. And what they have found is surprising, counterintuitive, and deeply fascinating. The answer, if there is one, lies not in abstract speculation but in quantum mechanics, in the nature of vacuum energy, in the structure of space-time itself. It lies in understanding what physicists really mean when they use the word nothing, because that word, as we will discover, does not mean what most people think it means. So as you settle into stillness, as your breathing begins to slow and your body relaxes, prepare yourself for a journey that will take us from the everyday understanding of emptiness to the quantum foam that underlies reality, from the singularity at the beginning of time to the possibility that time itself emerged from something that cannot quite be called nothing. We will explore how the universe might have begun not as a violation of the laws of physics but as a fulfillment of them, how creation might be perfectly consistent with conservation, how something and nothing might not be opposites but different aspects of the same underlying reality. This is not a story with a simple answer. It is a story of how science approaches the deepest mysteries, how each discovery opens new questions, how the boundary between nothing and something becomes less clear the more carefully we examine it. Welcome to the exploration of where everything came from, or perhaps more accurately, welcome to the discovery that the question itself needs to be reimagined. Welcome to the search for understanding what nothing really means in a universe governed by quantum uncertainty and cosmic expansion. Let us begin gently, slowly, with room for wonder and rest. There is something deeply uncomfortable about the question of whether the Big Bang came from nothing. It feels like asking the impossible, like trying to grab smoke or measure silence. How can we speak meaningfully about a state that, by definition, contains no things, no space, no time, no properties at all? And yet, this is precisely the question that modern cosmology forces us to confront. The discomfort begins with language itself. The word nothing is deceptively simple. In everyday speech, we use it constantly. There is nothing in the refrigerator. I have nothing to wear. Nothing happened today. But in each case, we do not really mean absolute nothingness. We mean an absence of something specific within a context that continues to exist. The refrigerator is still there. The closet remains. Time keeps flowing. True nothingness, philosophical nothingness, would be the absence of everything. No space to be empty within, no time in which absence could be noted. No laws of physics to govern what might or might not occur. No potential, no possibility, no framework whatsoever. It is a concept so complete in its negation that even thinking about it seems to require something, a mind doing the thinking, existing within time and space. This is why philosophers have struggled with the question for millennia. If you start with absolute nothing, not just empty space but no space at all, then how could anything ever begin? Nothingness has no properties, no mechanisms, no way to transition into something. It simply is not, completely and permanently, yet here we are. The universe exists. Matter, energy, space-time, galaxies, stars, planets, consciousness. All of it is manifestly present. So either the universe has always existed in some form, which pushes the question back without resolving it, or it somehow began, which seems to violate the principle that from nothing, nothing comes. Physics approaches this ancient puzzle not by solving it in the philosophical sense, but by redefining the terms. When physicists ask whether the universe could have come from nothing, they are not asking about philosophical nothingness, that complete absence of everything including the laws of physics themselves. They are asking about physical nothingness, the closest approximation to emptiness that the laws of physics permit. And this distinction, subtle though it may seem, changes everything. Physical nothing, in the language of quantum field theory, is what we call the vacuum. Not a vacuum in the everyday sense of empty space you could create by pumping air out of a chamber, but the quantum vacuum, the lowest energy state that the universe can have. And as we will discover, this quantum vacuum is very far from empty. It is filled with fields that permeate all of space. It seethes with quantum fluctuations. It contains energy. It has structure and properties. It can even, under the right conditions, give rise to particles, to space-time itself, to entire universes. When physicists say the Big Bang might have come from nothing, they are really saying it might have emerged from the quantum vacuum, from a state that has no particles or matter, but still has the potential for existence written into its fundamental nature. This is not cheating or moving the goalposts, though it might seem that way at first. It is recognizing that physics can only describe states that obey the laws of physics. If you ask about a state where the laws themselves do not exist, where logic and mathematics and causality break down completely, then you have stepped outside the domain where science can operate. But if you ask about the lowest energy state consistent with quantum mechanics and relativity, about what the universe looks like when you remove everything removable while still obeying the rules, then physics has a great deal to say, and what it says is surprising. The impossible beginning is impossible only if we insist on starting from absolute philosophical nothing. But if we start from the quantum vacuum, from the state that physics recognizes as the closest thing to nothing, then the beginning becomes not only possible but perhaps even inevitable. The vacuum is unstable in a deep sense. It fluctuates constantly. Particles appear and vanish. Energy is borrowed and returned. And under certain conditions, those fluctuations can grow, can inflate, can become the seed of an entire expanding universe. This is the core insight that makes the question of origins scientifically tractable. By recognizing that nothing in the physical sense is not the same as nothing in the philosophical sense, we can ask questions that observations can test, that mathematics can describe, that experiments can probe. We can ask whether the quantum vacuum has enough structure to give rise to spacetime. We can calculate whether conservation laws permit such a transition. We can search for signatures in the cosmic microwave background that would tell us about the earliest moments. We can propose mechanisms like inflation that connect the quantum scale to the cosmic scale. None of this tells us why the laws of physics exist in the first place, or why the quantum vacuum has the properties it does, or why there is something rather than absolute philosophical nothing. Those questions may lie forever outside the reach of science, or they may eventually yield to deeper theories we have not yet imagined. But what physics has accomplished is remarkable nonetheless. It has taken a question that seemed purely philosophical, beyond the reach of evidence and calculation, and has shown that at least part of it can be addressed scientifically. The origin of the universe is not completely mysterious. It is constrained by observation, guided by theory, and connected to the same quantum mechanics that explains atoms and chemistry and solid matter. The impossible beginning becomes merely improbable, or perhaps even probable, depending on the details of the quantum vacuum and the mechanisms of inflation. What seemed like a miracle, the appearance of everything from nothing, becomes a natural consequence of physical law. This is not to diminish the wonder of existence. If anything, it deepens it. The fact that the universe might have emerged from quantum fluctuations that the laws of physics themselves permit, creation, that conservation and symmetry and probability conspire to make something from almost nothing. This is as awe-inspiring as any traditional story of origins. The impossible beginning, examined carefully through the lens of physics, reveals itself not as an impossibility, but as a profound puzzle that we are slowly learning to solve. The question shifts from whether something can come from nothing to what kind of nothing physics describes, what properties that nothing must have, and how those properties connect to the universe we observe. As you rest now, breathing slowly, let this perspective settle. The beginning of everything is not beyond understanding. It is simply at the edge of what we currently know, in that frontier region where quantum mechanics meets cosmology, where the very small connects to the very large, where nothing turns out to be something after all. The impossible is only impossible until we understand it, and we are beginning to understand. To understand how we arrived at the question of whether the Big Bang came from nothing, we need to step back to a time when the question would have seemed absurd, a time when most scientists, including the greatest physicists of the age, assumed that the universe simply was eternal and unchanging, requiring no origin and no explanation for its existence. This was the prevailing view in the early 20th century. The cosmos was thought to be a vast, steady expanse of space filled with stars. Time stretched infinitely in both directions. Matter had always existed and would always exist. The universe was not a thing that began or would end. It was simply the eternal stage on which physical processes played out. This assumption was not unreasonable. Nothing in everyday experience suggested that the universe as a whole was dynamic. Stars moved in their courses, planets orbited, but the overall structure seemed permanent. The night sky looked much the same to early 20th century astronomers as it had to their predecessors centuries before. The idea of cosmic change, of the universe having a history, of everything once being compressed into a tiny region, was simply not part of the conceptual framework. Even the nature of the cosmos was misunderstood. What we now call galaxies were then known as spiral nebulae, faint smudges of light visible through telescopes. Most astronomers assumed they were clouds of gas within our own Milky Way. The possibility that they were separate island universes, each containing billions of stars, lay outside the bounds of serious consideration. The prevailing model was essentially Newtonian, though refined and extended. Isaac Newton had described a universe governed by gravity, where matter attracted matter across empty space. His laws worked beautifully for planets and moons, for falling apples and orbiting comets. Extended to the cosmos, they suggested an infinite, eternal distribution of matter, static on the largest scales, even as individual objects moved within it. There were problems with this picture, puzzles that troubled careful thinkers. If the universe were infinite and filled with stars, why was the night sky dark? Every line of sight should eventually hit a star, making the sky uniformly bright. This paradox, known as Olbers's paradox after the astronomer who popularized it, had no satisfactory solution within the eternal static model. But most physicists were not cosmologists. They focused on matter and energy, on atoms and radiation, on forces and fields. The universe as a whole was background, not subject. It simply existed, providing the arena in which physics occurred, but not itself requiring physical explanation. This all began to change in the early 1900s with the development of relativity. Albert Einstein's special relativity, published in 1905, revolutionized understanding of space and time, showing that they were not absolute but relative, interwoven into a single fabric called space-time. Motion affected time. Energy and mass were equivalent. The speed of light was the ultimate cosmic speed limit, but special relativity applied only to non-accelerating reference frames. Gravity, the force that shaped the cosmos on large scales, was still described by Newton's theory. separate from the new understanding of space-time. Einstein knew this was unsatisfying. Gravity should be incorporated into the relativistic framework. Space and time should not be mere background, but should interact with matter and energy. He worked on this problem for a decade. The mathematics was difficult, requiring tools that Einstein had to learn and adapt. The conceptual leaps were profound, but in 1915 he published his general theory of relativity, a complete reformulation of gravity not as a force but as the curvature of space-time itself. In this new picture, matter and energy curved space-time around them, and that curvature determined how other matter moved. Planets orbited the Sun not because of a force pulling them, but because the Sun curved space-time and they followed the straightest possible paths through that curved geometry. Gravity was geometry. Space-time was dynamic, responsive to what it contained. The implications were staggering. Space-time was no longer passive background. It could stretch, compress, ripple, and evolve. And most dramatically, when Einstein applied his equations to the universe as a whole, he found something unexpected and disturbing. The equations did not permit a static universe. If you filled space-time with matter uniformly, as seemed reasonable for a large-scale model, the equations predicted that space would either expand or contract. Gravity would pull everything together, causing collapse, unless some force counteracted it. There was no such force in the equations as Einstein had written them. This result troubled Einstein deeply. He, like everyone else, believed the universe was eternal and unchanging. The fact that his beautiful new theory predicted dynamism seemed like a flaw, so he modified the equations, adding a term he called the cosmological constant, a kind of repulsive force that could exactly balance gravity and hold the universe static. The cosmological constant was mathematically allowed, a term that could be added to the equations without violating their internal consistency. But it was arbitrary, chosen specifically to force the solution Einstein wanted. It felt artificial, a patch, rather than a natural consequence of the theory. Still, with this modification, Einstein could construct a model of an eternal, static universe, and for a time, this satisfied him and most physicists. The equations had been tamed, made to conform to expectations. The universe remained what it had always been thought to be, unchanging and eternal. But the universe had other ideas. Even as Einstein was adding his cosmological constant, other scientists were pursuing the implications of relativity, without that modification. Alexander Friedmann, a Russian mathematician, studied the original equations and found solutions describing universes that expanded or contracted. These were mathematical curiosities at first, not taken as physical descriptions of reality. Georges Lemaitre, a Belgian physicist and Catholic priest, went further. He proposed that if the universe was expanding now, then running time backward would show it contracting, becoming denser and hotter, eventually reaching a state of immense compression. He called this the primeval atom, a beginning point for the cosmos. These ideas were speculative. They rested on mathematics, not observation, and they contradicted the prevailing assumption of eternality. Most scientists remained skeptical. The universe was too grand, too permanent, to have simply begun at some point in the past. But observations were beginning to accumulate that would force a reckoning. Vesto Slipher, working at Lowell Observatory in Arizona, had measured the spectra of spiral nebulae and found that most showed redshifts, meaning their light was stretched toward longer wavelengths. This suggested they were moving away from us. At the time, the significance of this was unclear. Were these nebulae small and nearby, moving through the Milky Way? Or were they distant, and if so, what did their recession mean? The pieces were there, but no one had yet assembled them into a coherent picture. The stage was set for a revolution. The old assumptions of eternality and stasis were about to crumble. The universe was not what it seemed, and the question of origins, long thought to be purely philosophical or theological, was about to become a scientific question, grounded in observation and calculation. Where it all began, in terms of our modern understanding, was in this period of transition. The assumptions were still in place. The universe was still thought eternal, but the tools for overturning those assumptions, the equations of general relativity, the spectroscopic measurements, the philosophical willingness to imagine a dynamic cosmos, were coming together. Within 2 decades, the old picture would be shattered. The universe would be revealed as expanding, as having a history, as possessing an origin that could be traced backward in time. The question of whether the Big Bang came from nothing would become not a metaphysical puzzle but a scientific investigation. But in the early 1900s, that revolution still lay ahead. Scientists worked within the framework of eternality, assuming the universe had no beginning, required no explanation for its existence, simply was and always had been. It is striking how quickly this changed. Within a single generation, the entire conceptual landscape shifted. The eternal became temporal. The static became dynamic. The self-evident became questionable. And the origin of everything became a problem that physics could address. As you rest now, breathing deeply, consider this transformation. How assumptions we take for granted can be overturned by careful observation. How the universe can be stranger than our intuitions suggest. How the beginning of understanding often lies in recognizing that what we thought we knew was incomplete. Where it all began, for cosmology, was in letting go of eternality, in accepting that the universe might have a history, in being willing to follow the mathematics wherever it led, even if it led to conclusions that seemed impossible or absurd. The universe, it turned out, did not care about human intuitions or preferences. It had its own nature, and that nature was about to be revealed. Not eternal, but ancient. Not static, but expanding. Not self-explanatory, but puzzling, requiring explanation, inviting the question that would drive decades of research. If the universe is expanding now, what was it like in the past? And if we trace that expansion backward, where do we arrive? At a beginning? At something from nothing, the question was about to become unavoidable. The equations that would upend humanity's understanding of the cosmos were, in their way, beautiful. They connected geometry to matter, curvature to energy, and showed that space and time were not rigid containers but dynamic participants in physical processes. Yet hidden within their elegant mathematical structure was a prediction so unexpected that even their creator initially refused to accept it. Einstein's field equations of general relativity linked the curvature of space-time to the distribution of mass and energy. On one side of the equation was geometry, describing how space-time bent. On the other side was the stress-energy tensor, describing matter and radiation. The equality between them meant that matter told space-time how to curve, and space-time told matter how to move. When Einstein tried to apply these equations to the universe as a whole, assuming a uniform distribution of matter and no preferred direction, he expected to find a static solution. Space should be filled with galaxies at rest relative to one another, perhaps with small local motions but no overall expansion or contraction. This is what intuition and observation seemed to demand, but the mathematics refused to cooperate. The equations predicted instability. A universe filled uniformly with matter could not remain static. Gravity would cause it to collapse inward unless something prevented it. The natural solutions were either expansion, where space stretched and carried matter apart, or contraction, where everything fell together. This was deeply troubling. Not only did it contradict the prevailing view of an eternal cosmos, but it seemed to create a paradox. If the universe was contracting, why had it not already collapsed? If it was expanding, when did that expansion begin? Either way, the eternal static picture was incompatible with relativity as Einstein had formulated it. Faced with this conflict between his equations and his assumptions, Einstein made a choice that he would later call his greatest blunder. He modified the equations by adding a new term, the cosmological constant, represented by the Greek letter lambda. This term acted like a kind of anti-gravity, a repulsive force that increased with distance and could exactly balance gravitational attraction. With the cosmological constant carefully tuned to the right value, Einstein could construct a static model of the universe. The equations were satisfied. The cosmos remained eternal and unchanging. The mathematics had been brought into line with expectation, but the modification was artificial. The cosmological constant was not required by any principle or observation. It was added specifically to achieve a preconceived result, and even then, the static solution was unstable. Any small perturbation would cause it to begin expanding or contracting. It was balanced like a pencil on its point, theoretically possible but practically impossible to maintain. Other physicists, less invested in the static universe, began exploring what the unmodified equations predicted. Alexander Friedmann in Russia derived solutions describing expanding and contracting universes. His work was mathematical, not observational. He was exploring possibilities within the theory, not claiming to describe reality. But he showed that general relativity naturally led to dynamic cosmologies. Georges Lemaitre, working independently, reached similar conclusions. He went further, proposing that if the universe was expanding, then extrapolating backwards suggested a beginning, a point of origin where everything emerged from what he poetically called the primeval atom. This was the first articulation of what would later be called the Big Bang, though the name would not be coined for decades. Lemaitre's proposal was radical. It suggested not only that the universe was dynamic, but that it had a finite age, that time itself had a beginning. This contradicted not only scientific orthodoxy, but also raised deep philosophical and theological questions. If the cosmos had an origin, what caused it? What existed before? Could science even address such questions? Most scientists remained skeptical. The idea of a beginning seemed to violate the principle that from nothing, nothing comes. It required special initial conditions. It suggested a singularity, a breakdown of physics. The eternal static universe, despite the difficulties Einstein's equations posed, still seemed more reasonable. But while theorists debated, observers were making measurements that would tip the balance. Vesto Slipher had discovered that most spiral nebulae showed redshifts. Their spectral lines shifted toward longer wavelengths. If interpreted as Doppler shifts from motion, this implied recession, movement away from us. Edwin Hubble, working with the largest telescope in the world at the time, took the next crucial step. He measured distances to these spiral nebulae using Cepheid variable stars as standard candles. His results showed that the nebulae were not nearby clouds within the Milky Way, but separate galaxies millions of light years away. The universe was far larger than anyone had imagined. But more importantly, when Hubble compared distances to recession velocities, he found a clear relationship. The farther away a galaxy was, the faster it was receding. This was not random motion. It was a systematic pattern, exactly what would be expected if space itself was expanding, carrying galaxies apart like raisins in rising bread dough. Hubble published his results in 1929. The data were clear. The universe was expanding. The static, eternal cosmos was an illusion. The equations of general relativity, taken at face value without the artificial cosmological constant, had been right all along. When Einstein learned of Hubble's discovery, he reportedly said that adding the cosmological constant had been his greatest blunder. If he had trusted his equations, he could have predicted the expansion of the universe before it was observed. Instead, he had modified them to match an incorrect assumption. The spark of mystery was this. The equations knew something we did not. The mathematics contained truths that observation had not yet revealed, and that intuition rejected. General relativity predicted a dynamic universe, and reality confirmed it. This moment represents a profound shift in how science operates. Mathematics is not merely a tool for describing what we observe. It can predict phenomena we have not seen, guide us toward discoveries we did not anticipate, reveal truths that contradict common sense. The equations become a partner in discovery, not just a language for recording facts. The spark of mystery also ignited new questions. If the universe was expanding now, what was it like in the past? If we trace the expansion backward, where did we arrive? At a point of origin? At a singularity? At a beginning of time itself? And if so, what did that mean? Could physics describe such a state? Or did we reach the boundary where science ended and philosophy began? These questions would drive cosmology for the rest of the century. They would lead to discoveries of the cosmic microwave background, the theory of inflation, the realization that most of the universe is invisible dark matter and dark energy. They would transform cosmology from a speculative branch of philosophy to a precision science grounded in observation. But all of it traced back to this moment. Einstein's equations, initially resisted and artificially constrained, turned out to be correct. They predicted expansion. They suggested a beginning. They opened the door to asking whether the universe could have come from nothing. The spark of mystery was not just the discovery that the universe expands, it was the recognition that the cosmos has a history, that it changes, that it had a state different from the present. And with that recognition came the inevitable question. If the universe had a beginning, what preceded it? What caused it? What was the initial state? Physics could now address these questions, not with certainty, but with theories that could be tested, with models that made predictions, with frameworks that connected observation to deep principles. The mystery remained, but it had moved from pure philosophy into the realm of science. As you breathe slowly now, let this transition settle. The spark that ignited modern cosmology was a willingness to trust mathematics, even when it contradicted intuition, to follow evidence even when it led to uncomfortable conclusions, to ask questions that seemed unanswerable, and then to develop tools for answering them. The universe, it turned out, was not eternal. It had a beginning, and with that realization, the ancient question of origins became a scientific puzzle. The spark of mystery became the spark of discovery, when the evidence for an expanding universe became undeniable. The reaction among scientists and philosophers was not immediate acceptance, but a mixture of wonder and resistance. The implications were simply too vast, too strange, too contradictory to everything that had been assumed about the nature of reality. An expanding universe meant that the cosmos had a history. It meant that conditions in the past were fundamentally different from the present. It meant, most troublingly, that if you traced that expansion backward far enough, you would arrive at a state of incredible density and temperature, perhaps even a singularity where all the matter and energy of the universe was compressed into an infinitesimal point. This was not just a new fact to be added to the catalogue of knowledge, it was a complete reversal of the conceptual framework within which science had operated. The eternal was replaced by the temporal. The unchanging was revealed as dynamic. The self-evident permanence of the cosmos was shown to be an illusion, created by the brevity of human lifespans and the vastness of cosmic timescales. For some scientists, this was exhilarating. It meant that cosmology, the study of the universe as a whole, was not beyond the reach of scientific investigation. Questions about origins, age, and structure could be addressed with observations and calculations. The largest questions could be approached with the same rigour applied to atoms and forces. But for others, the expanding universe was deeply unsettling. It raised uncomfortable questions about causality and origins. If the universe began from a compressed state, what preceded that state? What caused it to begin expanding? Could physics describe conditions of such extreme density and temperature? Or would the laws themselves break down? Edwin Hubble himself, whose observations provided the crucial evidence, was cautious about interpretations. He presented the data, the relationship between distance and recession velocity, but was reticent to claim that this necessarily meant the universe was expanding. Perhaps there was some other explanation for the redshifts, some unknown physical process that stretched light without requiring motion. This caution reflected a broader uncertainty. The data were clear. Galaxies showed systematic redshifts proportional to their distance, but the implications were so profound that even the discoverer hesitated to fully embrace them. It was one thing to measure velocities. It was another to conclude that space itself was stretching, carrying everything apart. The philosophical implications were even more troubling. If the universe had a finite age, if it began at some point in the past, then time itself might have a beginning. What did it mean for time to begin? Could there be a before, if time did not yet exist? These questions seem to push against the boundaries of rational thought. Religious thinkers initially welcomed the idea of a beginning, seeing it as consistent with creation narratives. But many scientists were uncomfortable with anything that seemed to invoke supernatural explanations. If the universe began, did that imply a beginner? Was this a return to theology disguised as physics? Georges Lemaitre, who had proposed the primeval atom model, was both a physicist and a Catholic priest. He insisted that his scientific work was separate from his religious beliefs, that the beginning implied by physics was not the same as creation in the theological sense. Science described how the universe evolved from an initial state. It did not address why that state existed or what, if anything, came before it. But the conflation was difficult to avoid. The very language of beginnings carried theological overtones. Critics worried that accepting a cosmic origin would undermine the naturalistic foundation of science, that it would open the door to arguments about design and purpose. Arthur Eddington, a prominent physicist who had helped confirm general relativity through his observations of a solar eclipse, famously declared that the notion of a beginning was repugnant. He could not accept that the universe simply started, that time had a first moment, that there was nothing before. It violated his sense of how nature should work. Others proposed alternatives. Perhaps the universe was expanding now but had existed eternally, undergoing cycles of expansion and contraction. Perhaps there was no true beginning, only a transition from some previous state. Perhaps the redshifts had a different cause, one that did not require cosmic expansion. These alternatives were motivated as much by philosophical discomfort as by scientific evidence. The expanding universe challenged deep assumptions about permanence and causality. It suggested that the cosmos was not a fixed stage but an evolving system, one that might have emerged from conditions beyond our current understanding. The resistance was not simply obstinacy. It was a natural response to a radical claim. Extraordinary claims require extraordinary evidence, and while Hubble's observations were compelling, they were not initially overwhelming. Distances to galaxies were uncertain. The relationship between distance and velocity was approximate. Alternative explanations, however contrived, remained possible. Over time, additional evidence accumulated. More galaxies were measured at greater distances. The relationship between distance and recession velocity became more precisely defined. The pattern was too consistent, too clear, to be explained by anything other than expansion. The skeptics gradually yielded to the weight of data, but the sense of awe never disappeared. Even among those who accepted the expanding universe, there was profound wonder at the implications. The cosmos was not eternal. It had an age, now estimated at about 13.8 billion years. Everything we see, all the galaxies, all the stars, all the atoms, emerged from a state of incredible compression, heat. This was the Big Bang, though the name itself came later, coined by Fred Hoyle in a radio broadcast. Hoyle was actually a skeptic of the theory, and he used the term somewhat mockingly to describe a model he did not believe. But the name stuck, capturing the popular imagination even as it somewhat misrepresented the physics. There was no explosion in space. Space itself expanded. The awe was not just about the beginning, but about what the expanding universe implied for the future. If expansion continued indefinitely, galaxies would drift apart, stars would burn out, and eventually the universe would become cold and dark, a state of maximum entropy from which no further change was possible. The cosmos was not eternal into the future any more than into the past. This raised existential questions. If the universe had a beginning and would have an end, if everything was temporary on cosmic scales, what did that mean for human meaning and purpose? These were not scientific questions, but they could not be entirely separated from the scientific discovery. The expanding universe changed not just our knowledge, but our place in the cosmos. The disbelief gradually transformed into acceptance, and then into active investigation. Scientists began asking what the early universe was like. What processes occurred in its first moments? What signatures of those processes might still be detectable? The Big Bang became not just a fact, but a framework for research. Yet, even with acceptance, a residue of awe remained. The sheer scale of the expansion, the density and temperature of the early state, the fact that everything emerged from something almost incomprehensibly small and hot, all of this strained the limits of imagination. The mathematics described it, observations confirmed it, but grasping it intuitively remained difficult. The journey from disbelief to acceptance took decades. It required not just data, but a willingness to let go of cherished assumptions, to embrace a universe stranger than anyone had imagined, to accept that origins were not beyond scientific investigation but at its very heart. As you rest now, completely relaxed, let this sense of awe and transformation wash over you. The universe revealed itself as dynamic, historical, originated. What seemed impossible became fact. What seemed beyond science became its deepest question. The disbelief gave way not to certainty but to wonder, to the recognition that reality exceeds our expectations and that the cosmos is far more remarkable than static eternality could ever be. Once astronomers accepted that the universe was expanding, that it had a beginning in a hot, dense state, a profound contradiction emerged. It was not a contradiction within the mathematics or the observations. Those were consistent. It was a contradiction between physics and common sense, between what the evidence showed and what basic logic seemed to demand. The contradiction can be stated simply. How can something come from nothing? Every experience we have, every principle of causality we understand, suggests that things do not spontaneously appear. Objects do not pop into existence without cause. Energy cannot be created from emptiness. Effects require causes. Outcomes require prior states. The chain of causality is unbroken, yet the Big Bang seemed to violate this fundamental principle. If you trace the expansion of the universe backward, following the trajectories of galaxies as they converged, you arrived at a point roughly 14 billion years ago where everything was compressed into an infinitesimal region. Before that point, the equation suggested, time itself might not have existed. Space had not yet expanded. Matter and energy were confined to a state of such extreme density that the physics we understand breaks down. This singularity, as it came to be called, represented a boundary. Not just a physical boundary, but a conceptual one. At the singularity, the equations of general relativity produced infinities. Density became infinite. Curvature became infinite. Temperature became infinite. These infinities were signs that the theory had reached its limit, that it could not describe what lay beyond. But beyond was the wrong word. Beyond suggested another region of space or another moment of time. Yet if the singularity marked the beginning of space-time itself, there was no beyond. There was no before. There was, in the most literal sense, nothing. And from that nothing, everything emerged. This is the contradiction. Physics insists that causes precede effects, that states evolve from prior states, that the conservation of energy forbids creation ex nihilo. Yet cosmology seemed to require exactly that. The universe began, time began, space began. And before those beginnings, if before even makes sense, there was nothing. For some, this was evidence that the Big Bang model must be incomplete or incorrect. Perhaps there was no true beginning. Perhaps the universe bounced from a previous contracting phase. Perhaps time extended backward infinitely, and the apparent singularity was an artifact of our limited understanding. These alternatives were motivated not by observational contradictions, but by the philosophical discomfort with creation from nothing. For others, the contradiction pointed to the limits of language and intuition. Our concepts of causality and time are derived from experiences within the universe. They may not apply to the universe as a whole. Asking what caused the universe might be like asking what is north of the North Pole. The question presumes a framework that does not exist. But the contradiction remained troubling. It was not enough to say that our intuitions might be wrong. Science requires explanations, mechanisms, frameworks that connect observations to principles. Saying that the universe just began, with no prior cause, felt like giving up, like declaring a mystery unsolvable. This is where physics began to offer surprising insights. By carefully examining what was meant by nothing, by understanding the nature of the vacuum in quantum mechanics, by calculating the energy budget of the universe, scientists began to see that the contradiction might not be as absolute as it first appeared. The key realization was that physical nothing is not the same as philosophical nothing. In quantum field theory, the vacuum is not empty. It is filled with fields that permeate all of space. These fields fluctuate according to the uncertainty principle. They cannot be perfectly still or perfectly calm. Even in the absence of particles, the fields are there, seething with activity. This quantum vacuum has energy. It has properties. It has structure. Most importantly, it has the capacity to produce particles under the right conditions. Particle-antiparticle pairs constantly appear and disappear, borrowing energy briefly and then returning it. These virtual particles are not directly observable, but their effects are measurable. They shift atomic energy levels. They create forces between surfaces. They are real consequences of the vacuum's structure. If the quantum vacuum can produce temporary particles through fluctuations, might it also produce something more permanent under different conditions? Might a fluctuation, given the right circumstances, inflate into an entire expanding universe? This was the audacious proposal that began to address the contradiction. But even this left questions. Where did the quantum vacuum come from? Where did the fields come from? Where did the laws of physics that govern fluctuations come from? Each answer seemed to push the mystery back one step, without resolving it. Another insight came from considering energy conservation more carefully. In ordinary circumstances, energy is conserved. You cannot create it from nothing. But gravity, surprisingly, carries negative energy. When masses attract, their gravitational potential energy is negative. This means that in a system with both matter and gravity, the total energy might be zero. Positive energy from matter balanced by negative energy from gravity. If the universe as a whole has zero total energy, then it does not violate conservation by existing. It is not something created from nothing, but a balancing act where positive and negative cancel. The universe could arise from a fluctuation because the total cost is zero. No energy needs to be borrowed or supplied. The ledger balances perfectly. This was a profound realization. The contradiction between conservation laws and cosmic origins might dissolve if the total energy of the universe is zero. Creation from nothing becomes not a violation of physics but a consequence of it. The universe is permitted by the same laws that seem to forbid it. Yet even this elegant solution had limits. It explained how the energy budget could balance. It did not explain why the laws of physics exist in the form they do, why the quantum vacuum has its properties, or why anything exists at all rather than absolute philosophical nothing. The contradiction, examined carefully, split into layers. There was the apparent contradiction between something and nothing, resolved by understanding that physical nothing is not empty. There was the apparent contradiction between conservation and creation, resolved by understanding that gravity carries negative energy. But beneath these layers lay deeper questions about the existence of laws, the nature of necessity, and the boundary between physics and metaphysics. Different thinkers drew different conclusions. Some argued that physics had successfully explained how the universe could arise from nothing, that the mystery was solved within the framework of quantum mechanics and relativity. Others argued that physics had merely pushed the mystery back, replacing one form of nothing with another, the quantum vacuum, which itself required explanation. The contradiction also highlighted the difference between how and why questions. Physics excels at how questions. How did the universe expand? How did structure form? How do particles acquire mass? These can be answered with observations, equations, and experiments. But why questions? Why do the laws exist? Why is there something? Are harder. They may lie outside the domain of science, or they may simply await theories we have not yet developed. What became clear was that the contradiction was not a flaw in the Big Bang model, but a signpost pointing toward deeper physics. The singularity, where equations broke down, indicated that general relativity was incomplete. At extreme densities, quantum effects must matter. A theory of quantum gravity, combining relativity and quantum mechanics, was needed to describe the earliest moments. Such a theory might replace the singularity with something finite, might show how time emerged from a timeless state, might demonstrate that what appears as creation from nothing is actually a transition from one quantum state to another. The contradiction would dissolve not by abandoning physics, but by extending it. As you breathe deeply now, feeling your body completely at rest, consider this contradiction not as a problem, but as an invitation to think more carefully about what nothing means, about what creation requires, about how the universe can be both comprehensible and mysterious. The contradiction between something and nothing is not a wall but a doorway, leading deeper into the nature of existence itself. As physicists grappled with the question of whether the Big Bang came from nothing, different frameworks emerged for thinking about what nothing might mean and how something could arise from it. These were not mere philosophical speculations, but scientific theories grounded in observation, constrained by mathematics, and connected to the broader structure of physics. The first distinction to make is between philosophical nothing and physical nothing. This distinction is not semantic hair-splitting, but gets to the heart of what science can and cannot address. Philosophical nothing is the complete absence of everything. No space, no time, no matter, no energy, no laws of physics, no potential for anything to exist. It is pure non-existence, absolute emptiness, the void in its most radical sense. This is what most people mean when they ask whether the universe came from nothing. But philosophical nothing is impossible for physics to describe. Science operates by finding patterns, writing equations, and testing predictions. All of these require some framework, some structure, some rules. Philosophical nothing has none of these. It is not a state that physics can model because there is nothing to model, no properties to describe, no dynamics to calculate. This is why physicists, when they talk about the universe arising from nothing, mean something different. They mean physical nothing, the quantum vacuum, the lowest energy state that the laws of physics permit. This is very far from philosophical nothing because it has structure, properties, and dynamics. The quantum vacuum is filled with fields. The electromagnetic field permeates all of space. The Higgs field gives particles their mass. Other fields correspond to the forces and particles of nature. These fields cannot be turned off or removed. They are woven into the fabric of reality. Moreover, these fields are not static. According to the uncertainty principle, they must fluctuate. A field that was perfectly calm, with no variation at all, would violate quantum mechanics. Energy and time, like position and momentum, are subject to uncertainty relations. This means that over short time scales, energy can fluctuate, particles can appear and vanish, and the vacuum seethes with activity. These quantum fluctuations are not hypothetical. They produce measurable effects. The Casimir effect, where two metal plates in a vacuum are pushed together by fluctuations, has been observed in laboratories. The Lamb shift, a tiny adjustment in the energy levels of hydrogen, results from the electron interacting with vacuum fluctuations. Precision measurements of particle properties show contributions from virtual particles that briefly exist and then disappear. So the quantum vacuum, far from being empty, is a restless sea of fields and fluctuations. It is the closest thing to nothing that physics recognizes, but it is already something. It has energy, structure, and the capacity to produce effects. This leads to the first major theory addressing cosmic origins: quantum cosmology. In this framework, the universe arises from a fluctuation in the quantum vacuum. Just as particle-antiparticle pairs can briefly appear, so too might a small region of space-time inflate from the vacuum, given the right conditions. The key insight is that quantum mechanics allows borrowing energy for short times as long as that energy is returned. In normal circumstances, fluctuations remain small and brief. But if a fluctuation produces a region with properties that drive rapid expansion, inflation, then that region can grow, generate more energy, and become a full universe. This does not violate conservation because the total energy remains zero. The positive energy of matter and radiation is balanced by the negative gravitational energy of the expanding space. The universe is a fluctuation that costs nothing to create because its total energy content is zero. Alan Guth, who developed the theory of inflation, emphasized this balance. Inflation creates enormous amounts of matter and radiation, but it also creates an equal amount of negative gravitational potential energy. The book's balance. Conservation is maintained. Another framework comes from considering the nature of space-time itself. In general relativity, space and time are not absolute background, but dynamic entities that respond to matter and energy. At extreme densities, quantum effects on space-time become important. A complete theory requires quantum gravity, a synthesis of relativity and quantum mechanics. String theory offers one approach. It suggests that the fundamental constituents of reality are tiny, vibrating strings in higher dimensional space. In this picture, the Big Bang singularity is smoothed out by stringy effects. Instead of infinite density, there is a finite maximum density, where new physics takes over. The universe might have emerged not from a singularity, but from a previous state, perhaps a collision of higher dimensional membranes. Loop quantum gravity takes a different path. It proposes that space-time itself is quantized, made of discrete units like atoms are made of particles. There is a smallest possible volume, a quantum of space. At the Planck scale, about 10 to the minus 35 meters, space-time has a granular structure. In this framework, the Big Bang is replaced by a Big Bounce. As the universe contracts, it reaches the Planck density where quantum gravitational effects create a repulsive force, preventing further collapse. Instead of a singularity, there is a bounce, a transition from contraction to expansion. Time extends backward through the bounce into a previous phase. The Hartle-Hawking no-boundary proposal offers yet another perspective. Stephen Hawking and James Hartle suggested that near the beginning, time becomes like space. In ordinary space-time, time is different from space, flowing forward while space extends in 3 dimensions. But in their model, this distinction blurs. Time becomes another spatial dimension. In this picture, asking what happened before the Big Bang is like asking what is south of the South Pole. The question presumes a direction that does not exist. The universe has no temporal boundary, no edge in time. Not because it extends infinitely backward, but because time itself has a different character near the origin. Each of these theories addresses the problem of nothing in different ways, but they share common features. They all recognize that philosophical nothing is outside the domain of physics. They all start from physical nothing, the quantum vacuum or quantum spacetime. They all invoke quantum mechanics to permit fluctuations or transitions that would be forbidden in classical physics. And they all aim to show that the universe could arise naturally, without violating conservation laws or requiring external causes. Critics point out that these theories do not fully solve the problem. They replace one form of nothing with another. The quantum vacuum is not nothing. Quantum fields are not nothing. Laws of physics are not nothing. So, in what sense has the universe come from nothing? Defenders respond that physics can only describe states consistent with the laws of physics. If you ask about a state where the laws do not exist, you have stepped outside science. The relevant question is not whether the universe came from absolute philosophical nothing, which may be incoherent, but whether it could arise from the simplest possible state consistent with quantum mechanics. This debate highlights a tension between physics and philosophy. Philosophers want ultimate explanations, accounts that rest on no prior assumptions. Physicists seek explanations within frameworks of law and observation. The two goals may not be fully compatible. What the theories show is that within the framework of quantum mechanics and relativity, the universe can arise from simple initial conditions without violating conservation, without requiring external input, and without invoking miraculous exceptions to natural law. Whether this counts as something from nothing depends on how strictly you define nothing. The practical consequence is that cosmology has moved from pure speculation to testable science. The theories make predictions about the cosmic microwave background, about the spectrum of fluctuations, about gravitational waves from inflation. Observations can test these predictions. ruling out some models and supporting others. As you rest deeply now, let these theories settle without strain. They show that nothing is not simple, that the boundary between existence and non-existence is blurrier than everyday intuition suggests, and that the question of origins, ancient and profound, has become a scientific investigation. The theories do not answer every question, but they show that asking how the universe began is not futile, that physics can reach toward the deepest mysteries even if it cannot fully grasp them. Understanding whether the universe could arise from nothing required more than philosophical debate or mathematical speculation. It demanded experimental evidence, careful observations, and the patient pursuit of phenomena that existed at the boundary between the visible and invisible, between matter and emptiness, between something and nothing. The pursuit began with trying to understand what empty space actually is. In classical physics, a vacuum was simply the absence of matter. Pump all the air out of a chamber, remove every atom, and you had emptiness. But quantum mechanics suggested something far stranger. Even in the absence of particles, even in a perfect vacuum, something remained. The first hints came from theoretical work in the 1920s and 30s. When physicists applied quantum mechanics to the electromagnetic field, they found that the field could never be completely still. The uncertainty principle, which forbids knowing both position and momentum exactly, also applies to fields. A perfectly calm field would violate quantum uncertainty. Therefore, fields must fluctuate even in their lowest energy state. These fluctuations were initially considered mathematical curiosities, tools for calculation rather than physical phenomena. But gradually, physicists realized they had real consequences. The vacuum was not empty, but filled with ephemeral activity, virtual particles appearing and vanishing in fractions of a second. The pursuit of understanding these vacuum fluctuations took decades. It required developing quantum field theory, a framework that treated particles as excitations of underlying fields. In this picture, an electron is a ripple in the electron field, a photon is a ripple in the electromagnetic field, and the vacuum is the state where all fields are in their lowest energy configuration, still fluctuating but without permanent particles. One of the first experimental confirmations came from the Lamb shift, discovered in 1947. Willis Lamb measured the energy levels of hydrogen atoms with extraordinary precision and found a tiny discrepancy from what simple quantum mechanics predicted. The explanation involved the electron interacting with vacuum fluctuations, with the seething activity of the electromagnetic field even in empty space. This was a turning point. The vacuum was not a theoretical abstraction, but something with measurable physical effects. Empty space was not empty. It had structure and properties that influenced matter. The pursuit continued with predictions about forces created by vacuum fluctuations. In 1948, Hendrik Casimir predicted that two uncharged metal plates placed close together in a vacuum would experience an attractive force. The reason was subtle. Between the plates, only certain wavelengths of vacuum fluctuations could exist, those that fit exactly between the boundaries. Outside the plates, all wavelengths were possible. This created a pressure difference, pushing the plates together. The Casimir effect was finally measured in 1958, confirming the prediction. Two plates with nothing between them, no particles, no fields that we could switch on or off, were pushed together by the quantum activity of empty space. The vacuum had energy and could exert forces. These discoveries fueled the pursuit of understanding vacuum energy more generally. Had energy? How much? Calculations using quantum field theory gave alarming results. Summing over all possible fluctuations at all possible wavelengths produced infinite energy density. Something was clearly wrong with the calculation. Physicists developed techniques called renormalization to handle these infinities, essentially subtracting away the divergences and focusing on measurable differences. This worked for calculating particle properties but left the absolute value of vacuum energy uncertain. The theory suggested it should be enormous, but observations showed it was either zero or incredibly small. This became known as the cosmological constant problem, one of the deepest puzzles in physics. The vacuum energy should contribute to the expansion of the universe through Einstein's equations. Too much energy, and the universe would expand too rapidly for galaxies to form. Too little, or negative energy, and it might collapse. Yet observations showed the universe was close to the critical density, suggesting the vacuum energy was finely tuned to an extraordinary degree. The pursuit of understanding vacuum energy took on new urgency in the 1990s, when observations of distant supernovae revealed that the expansion of the universe was accelerating, not slowing down as expected. The simplest explanation was that space itself contained energy, a dark energy driving the acceleration, and the leading candidate for dark energy was precisely the vacuum energy predicted by quantum mechanics. Suddenly, the vacuum was not just a theoretical curiosity, but the dominant component of the universe's energy budget. Empty space was not passive background, but an active participant in cosmic evolution, driving galaxies apart and determining the ultimate fate of the cosmos. The pursuit also extended to understanding quantum fluctuations in the early universe. If the vacuum fluctuated even now, in the relatively calm present, what must it have been like in the first moments after the Big Bang, when energies were extreme and space-time itself was forming? Alan Guth's theory of inflation, developed in the 1980s, suggested that a special field, the inflaton, underwent quantum fluctuations in the earliest moments. These fluctuations were stretched by the rapid expansion of inflation to cosmic scales, becoming the seeds of galaxies. What began as microscopic quantum noise ended as the large-scale structure of the universe. This idea connected the pursuit of understanding vacuum physics with cosmology. The quantum vacuum was not just relevant to particle physics, but to the origin and structure of the cosmos itself. The fluctuations could be seen, frozen into the pattern of temperature variations in the cosmic microwave background, a direct observational link between quantum mechanics and the universe at its largest scales. Experiments at particle accelerators added another dimension to the pursuit. When particles collide at high energies, they probe the structure of the vacuum at small scales. What appears as empty space at low energies might reveal structure at higher energies. The discovery of the Higgs boson in 2012 confirmed that the Higgs field permeates the vacuum, giving particles their masses. Without this vacuum structure, matter as we know it could not exist. The pursuit also involved searching for signatures of quantum gravity. At the Planck scale, about 10 to the minus 35 meters, quantum effects on spacetime itself should become important. At this scale, the smooth geometry of relativity might give way to a foamy, granular structure. Space and time might not be continuous but discrete, made of fundamental units. While direct observation of the Planck scale is impossible with current technology, indirect signatures might appear in the cosmic microwave background or in the properties of gravitational waves. The pursuit of detecting these signatures continues, with each new satellite mission and detector providing more sensitive probes of the earliest moments. Theorists pursued different approaches to quantum gravity. String theory suggested that at high energies, spacetime has extra dimensions, and that fundamental objects are strings rather than points. Loop quantum gravity proposed that spacetime itself is quantized. Each approach offered different pictures of what the vacuum might be at the deepest level. The pursuit was not just experimental and theoretical, but also computational. Simulations of the early universe, starting from quantum fluctuations and following the evolution through inflation and structure formation, tested whether the theories could reproduce observations. Supercomputers modeled billions of particles interacting under gravity, showing how tiny initial fluctuations grew into galaxies and clusters. Each line of pursuit, experimental, observational, theoretical, and computational, added pieces to the puzzle. The vacuum was not empty, but filled with fields and fluctuations. It had energy that affected cosmic expansion. It provided the seeds for cosmic structure. It contained hidden dimensions or quantum geometry at the smallest scales. Understanding the vacuum meant understanding the deepest nature of reality. The pursuit also revealed how interconnected physics had become. Questions about vacuum energy connected particle physics to cosmology. Understanding quantum fluctuations required both quantum mechanics and general relativity. explaining the origin of structure linked the smallest scales to the largest. The pursuit of understanding nothing had become the pursuit of understanding everything. What emerged from decades of work was a picture radically different from the classical notion of empty space. The vacuum was dynamic, structured, and essential. It was the stage on which physics played out, but it was also an active participant, influencing particles, driving expansion, seeding galaxies. Nothing. Examined carefully, it turned out to be something profound. As you breathe slowly now, completely relaxed, let the pursuit itself become a source of calm. For decades, scientists worked patiently to understand the vacuum, each experiment adding clarity, each theory refining understanding. The pursuit was not about quick answers, but steady progress. Not about certainty, but about approaching truth through careful investigation. The vacuum, like the mind settling into sleep, is not empty but quietly active, not nothing but a field of potential from which everything can emerge. After decades of theoretical speculation about vacuum energy and quantum fluctuations, physics reached a point where ideas could be tested against observation. The data, accumulated from particle accelerators, astronomical surveys, and precision measurements in laboratories, transformed abstract concepts into concrete evidence. What emerged was a picture of empty space, far stranger than anyone had imagined. The first category of data came from atomic physics. When Willis Lamb measured the energy levels of hydrogen in 1947, he found a small but unmistakable deviation from theoretical predictions. The electron orbiting the hydrogen nucleus should have occupied certain energy levels determined by quantum mechanics, but the measured values were slightly off. The explanation involved vacuum fluctuations. The electron, even as it orbited, was constantly interacting with the ephemeral activity of the electromagnetic field. Virtual photons appeared and disappeared, and these interactions shifted the electron's energy by a tiny but measurable amount. The Lamb shift, as it came to be known, was about 1 part in a million, but it could be measured with precision, and it matched theoretical calculations exactly. This was data showing that the vacuum was not empty. Something in empty space was affecting the behavior of electrons. That something was the quantum fluctuations of the electromagnetic field, the seething activity that could never be turned off. Another source of data came from measuring the magnetic moment of the electron. In quantum mechanics, particles have an intrinsic property called spin, and this spin creates a magnetic field. The strength of that field can be calculated and measured, but when physicists calculated the electron's magnetic moment with extreme precision, they found that virtual particles, the temporary fluctuations in the vacuum, contributed to the result. The agreement between theory and experiment is astonishing. The magnetic moment of the electron is known to better than 1 part in a trillion, and the theoretical calculation, which includes contributions from vacuum fluctuations of photons, electrons, and even heavier particles, matches that precision. This is one of the most accurately verified predictions in all of science, and it depends critically on the vacuum being full of activity rather than empty. The Casimir effect provided another form of data. In 1948, Hendrik Casimir predicted that 2 parallel metal plates in a vacuum would attract each other due to vacuum fluctuations. Between the plates, only certain wavelengths could exist, while outside, all wavelengths were possible. This created a net force pushing the plates together. The effect was finally measured precisely in 1958, and subsequent experiments refined the measurement. The force is tiny, only significant when the plates are extremely close, but it is real and measurable. 2 objects with nothing between them, no particles, no gas, no fields we control, are pushed together by the quantum structure of empty space. Data from cosmology added a larger scale perspective. In 1998, 2 teams of astronomers studying distant supernovae made a surprising discovery. The supernovae appeared fainter than expected, suggesting they were farther away than standard expansion models predicted. The only way to explain this was if the expansion of the universe was accelerating, not slowing down. An accelerating expansion required some form of energy, pushing space apart, counteracting gravity. The simplest candidate was vacuum energy. the energy inherent in empty space itself. If the vacuum had a positive energy density, it would act like a cosmological constant, driving expansion. The data from supernovae provided the first strong evidence that this vacuum energy was real and significant. Further observations confirmed the acceleration. The cosmic microwave background, measured by satellites like WMAP and Planck, showed patterns consistent with a universe dominated by dark energy. Galaxy surveys mapped the distribution of matter over large volumes, and the clustering patterns matched predictions for a universe with vacuum energy contributing about 70% of the total energy density. The data converged from multiple independent sources. Supernovae, the microwave background, galaxy clustering, and even the properties of gravitational lensing all pointed to the same conclusion. The universe contains a mysterious dark energy, and the leading candidate is the energy of the vacuum itself. But there was a puzzle. When physicists calculated how much vacuum energy there should be based on quantum field theory, they got an answer far larger than observations allowed. The discrepancy was not small. Naive estimates suggested the vacuum energy should be 10 to the 120 times larger than the measured value. This is the cosmological constant problem, one of the most profound mysteries in physics. The data showed that vacuum energy exists, that it affects cosmic expansion, and that it dominates the energy budget of the universe. But the data also showed that the amount is incredibly small compared to theoretical expectations. Explaining this discrepancy remains an open challenge. Data from particle accelerators added another dimension. When high-energy particles collide, they can produce showers of new particles. These processes involve virtual particles, temporary fluctuations in the vacuum that mediate interactions. The rates and patterns of particle production depend on how the vacuum behaves at high energies. The discovery of the Higgs boson in 2012 provided crucial data about the vacuum. The Higgs field permeates all of space, and particles acquire mass by interacting with this field. The data from the Large Hadron Collider confirmed that the Higgs mechanism operates as predicted, that the vacuum is structured by the Higgs field, and that this structure is essential to the existence of matter. Precision measurements of rare particle decays provided data about vacuum fluctuations involving heavier particles. The decay rates depended on contributions from virtual top quarks, W bosons, and other particles that briefly appeared in the vacuum before disappearing. The measured rates matched predictions, confirming that even particles too heavy to create directly in accelerators contribute through their virtual presence in the vacuum. Data also came from astrophysics. Observations of pulsars, rapidly rotating neutron stars, showed timing patterns that could be explained only if the vacuum had certain properties. Searches for gravitational waves, ripples in space-time from colliding black holes, provided new ways to probe the structure of the vacuum at extreme energies and curvatures. Each dataset, from atomic physics to cosmology, from particle accelerators to astronomical surveys, added evidence that the vacuum is not empty but filled with fields, fluctuations, and energy. The data transformed vacuum physics from speculation to established science. But the data also raised new questions. Why is the vacuum energy so small? Why is it fine-tuned to a value that allows the universe to be hospitable to structure and life? Could there be multiple vacuums, each with different properties, and we inhabit one that permits complexity? The data also constrained theories. Models of inflation made predictions about the spectrum of fluctuations in the cosmic microwave background. The data showed that the fluctuations were nearly scale invariant, matching inflation's predictions but ruling out alternatives. The precise pattern of peaks in the microwave background spectrum tested the composition of the universe, confirming the presence of dark matter and dark energy. Searches for primordial gravitational waves, predicted by some versions of inflation, continued to push the sensitivity of detectors. While a definitive detection had not yet occurred, the data set upper limits that constrained how energetic inflation could have been. Each new measurement tightened the bounds. The data also connected quantum mechanics to cosmology in direct ways. The fluctuations seen in the cosmic microwave background trace back to quantum fluctuations in the inflaton field, stretched to cosmic scales by exponential expansion. This was not theoretical speculation, but observational fact. The seeds of galaxies were quantum in origin, and the data showed their fingerprints across the sky. As you rest deeply now, let the solidity of the data bring comfort. These are not vague ideas or untestable speculations. They are measurements, precise numbers, patterns in observations that multiple instruments confirm. The vacuum is not empty, and we know this not from philosophy but from data. The universe contains vacuum energy, and we have measured its effects. The cosmic structure arose from quantum fluctuations, and we have mapped their imprint. The data transforms mystery into knowledge, guiding understanding toward truth. Beneath all the observations of vacuum fluctuations and quantum fields, beneath the measurements of particle properties and cosmic expansion, lay a truth that fundamentally changed how physicists understood the universe. The hidden truth was that most of what exists is invisible, that the universe we see is only a small fraction of what is there, and that understanding nothing requires understanding the invisible something that dominates reality. The story of this hidden truth began not with cosmology but with astronomy. In the 1930s, Fritz Zwicky studied clusters of galaxies and measured how fast individual galaxies moved within those clusters. He applied the virial theorem, a relationship between kinetic energy and gravitational potential energy, to estimate the mass needed to hold the cluster together. The result was shocking. The visible galaxies, all the stars and gas he could detect, accounted for only a fraction of the mass required. There was not enough visible matter to explain the motions. Either Newton's laws were wrong, or most of the mass in the cluster was invisible, not emitting or absorbing light. Zwicky called this unseen mass dark matter, but his discovery was largely ignored for decades. It seemed too strange, too contrary to expectations. Surely the mass we saw should be most of the mass there was. The idea that the universe was filled with invisible matter that outweighed the visible by factors of 10 seemed implausible. But evidence accumulated. In the 1970s, Vera Rubin studied rotation curves of spiral galaxies, measuring how fast stars orbit at different distances from the galactic center. Newton's laws and general relativity both predicted that stars farther out should move more slowly, just as outer planets in the solar system orbit more slowly than inner ones. Instead, Rubin found that rotation speeds stayed roughly constant, even at large distances. Stars far from the center moved just as fast as those closer in. The only explanation was that galaxies were embedded in halos of dark matter, invisible mass extending far beyond the visible stars. The dark matter provided additional gravitational pull, keeping outer stars moving faster than they otherwise would. Further observations confirmed the pattern. Every spiral galaxy studied showed flat rotation curves. Elliptical galaxies showed similar evidence in the velocities of their stars. Clusters of galaxies showed it in the motions of member galaxies and in the temperature of hot gas filling the space between them. Everywhere astronomers looked, dark matter was required to explain what they saw. Gravitational lensing provided another line of evidence. Einstein's general relativity predicted that mass bends light, that the path of a photon curves when passing near a massive object. Astronomers could use this effect to map the distribution of mass in galaxy clusters by observing how they distort the images of background galaxies. The maps revealed that the mass distribution was much more extended than the visible matter. Dark matter halos surrounding clusters could be traced through their gravitational effects, even though the matter itself emitted no light. The evidence was overwhelming. The universe contained vast amounts of invisible matter. Estimates suggested that dark matter outweighs ordinary matter by a factor of about 5 to 1. All the stars, planets, gas, and dust we can see make up only about 15% of the total matter. The rest is dark, invisible to telescopes operating at any wavelength. What is dark matter made of? Decades of research have not yet provided a definitive answer. It is not ordinary atoms. It does not interact with light. It does not clump into stars or planets. It passes through ordinary matter, almost without interaction, detectable only through gravity. Leading candidates include exotic particles left over from the early universe, produced in the hot dense conditions shortly after the Big Bang. WIMPs, weakly interacting massive particles, are one possibility. Axions, much lighter hypothetical particles, are another. Despite extensive searches using underground detectors, particle accelerators, and satellite observations, no direct detection has been confirmed. Yet dark matter is essential to understanding cosmic structure. Computer simulations show that without dark matter, galaxies and galaxy clusters could not have formed. The universe would be too smooth, with insufficient gravity to pull matter together into the structures we observe. Dark matter provides the gravitational scaffolding on which visible matter accumulates. But dark matter is only part of the hidden truth. An even larger component was discovered through observations of distant supernovae. In 1998, astronomers found that the expansion of the universe was accelerating. This required some form of energy with unusual properties, energy that did not clump like matter but spread uniformly through space, creating a repulsive effect that pushed galaxies apart. This dark energy, as it came to be called, appears to make up about 70% of the total energy density of the universe. Combined with dark matter at about 25%, ordinary matter contributes only about 5%. The visible universe, everything we can see with telescopes, is a tiny fraction of what exists. The leading candidate for dark energy is vacuum energy, the energy inherent in empty space itself. Quantum field theory predicts that the vacuum has energy, and Einstein's equations show that this energy would contribute to cosmic expansion. The measured value of dark energy is consistent with it being vacuum energy, though the theoretical prediction vastly exceeds the observed value. The hidden truth is that the universe is dominated by components we do not fully understand. Dark matter is invisible but detectable through gravity. Dark energy is even more mysterious, detectable only through its effect on cosmic expansion. Together they make up 95% of the universe, while ordinary matter, the stuff of stars and planets and people, is a minor component. This realization transformed cosmology. Understanding the universe required understanding dark matter and dark energy. The evolution of cosmic structure, the fate of the universe, the nature of space itself, all depended on these hidden components. What appeared to be the main story, the visible matter we see, was actually a subplot in a larger narrative dominated by the invisible. The hidden truth also connected to the question of origins. If the universe arose from quantum fluctuations in the vacuum, then understanding vacuum energy was essential. If dark matter was produced in the early universe, then conditions at the Big Bang determined its abundance. The hidden components were not separate mysteries but integral parts of the cosmic story. It also raised philosophical questions. If most of the universe is invisible, what does it mean to observe or know the cosmos? Science had always relied on observation, but now the majority of reality was beyond direct detection. We inferred its presence through its effects, through gravity and expansion, but we could not see it or touch it or capture it in laboratories. Yet science had adapted. The hidden components were no less real for being invisible. Their effects were measurable. Their properties were constrained by observations. Theories made predictions that could be tested. The invisible became knowable through indirect evidence, showing that reality extends beyond what our senses reveal. As you breathe deeply now, let this hidden truth settle without alarm. Most of what exists is invisible, but that does not make it unknowable. Dark matter shapes galaxies. Dark energy drives expansion. Vacuum energy fills space. Each is real. Each affects the cosmos. Each contributes to the universe we inhabit. The hidden truth is not that reality is mysterious beyond comprehension, but that it is richer than appearances. Suggests that nothing is not empty, and that something includes far more than we see. The accumulation of evidence about vacuum fluctuations, dark matter, dark energy, and quantum fields triggered a fundamental shift in how physicists understood the nature of reality. This was not merely a collection of new facts to be added to existing knowledge. It was a paradigm shift, a transformation of the conceptual framework itself, changing what it meant to talk about nothing, something, and the space between them. Before this shift, the prevailing view treated empty space as essentially passive. Space was the stage on which physics happened. the background against which matter and energy moved and interacted. The vacuum was defined by absence, by what was not there rather than by any intrinsic properties. Removing everything from a region left you with nothing, and nothing had no structure, no dynamics, no interesting physics. This view made sense in classical physics. Newton's mechanics treated space as an absolute container, fixed and unchanging. Maxwell's electromagnetism described fields propagating through space, but space itself remained passive. Even early quantum mechanics, though it introduced uncertainty and probability, did not fundamentally change the picture of empty space as inert background. The paradigm shift occurred gradually as quantum field theory matured and cosmological observations accumulated. Each piece of evidence added pressure to the old framework until it could no longer accommodate the facts. What emerged was radically different. In the new paradigm, the vacuum is not empty but full. It is filled with fields that cannot be removed or turned off. These fields are not added on top of space but are woven into its fabric. The electromagnetic field, the Higgs field, and all the others extend everywhere, permeating what we call empty space. Moreover, these fields are not static. They fluctuate according to the uncertainty principle, constantly producing temporary particles and antiparticles that appear and disappear. The vacuum seethes with activity at scales too small and times too brief to observe directly. But this activity has real, measurable consequences. This fundamentally changed what physicists meant by nothing. Physical nothing is not philosophical nothingness, the complete absence of everything. It is the quantum vacuum, the lowest energy state of the fields, still buzzing with fluctuations, still possessing energy, still capable of affecting particles and driving cosmic expansion. The paradigm shift also changed how physicists thought about particles. In the old view, particles were primary, the fundamental entities from which everything was built. Fields were secondary, mathematical tools for describing how particles interacted. In the new paradigm, fields are primary. Particles are excitations of fields, temporary ripples in an underlying medium that extends through all of space. An electron is not a little ball, but an excitation of the electron field. A photon is an excitation of the electromagnetic field. Even the vacuum, with no particles present, contains all the fields in their lowest energy states. Particles come and go, but the fields remain. This inversion of priorities was profound. It meant that the vacuum was not defined by the absence of particles, but by the presence of fields in their ground state. Nothing became something, a state with definite properties and dynamics. The paradigm shift extended to cosmology. The discovery of dark energy, likely vacuum energy, showed that empty space had a large-scale effect on the universe's evolution. The vacuum was not merely a local phenomenon affecting atomic energy levels, but a cosmic player driving the accelerated expansion of space itself. This challenged the notion that space was passive background. If vacuum energy contributed to expansion, then space had dynamic properties, an energy density that resisted being set to zero. The cosmological constant, which Einstein had added to his equations as an artificial fix, turned out to describe a real physical effect: the energy of the quantum vacuum. The paradigm shift also affected how physicists thought about origins. In the old paradigm, asking how the universe could arise from nothing seemed to pose an insurmountable problem. From absolute nothingness, with no properties and no dynamics, no mechanism could produce something. Creation from nothing violated causality and conservation. But in the new paradigm, the question changed. The relevant nothing was not philosophical nothingness, but the quantum vacuum. And the quantum vacuum, far from being inert, was a restless sea of fields and fluctuations capable of giving rise to particles, space, and time under the right conditions. Inflation theory showed how a small region of vacuum could undergo exponential expansion, stretching quantum fluctuations to cosmic scales and generating the matter and energy that filled the universe. The mechanism was natural, following from quantum field theory and general relativity without requiring external intervention or miracles. The paradigm shift meant that creation from nothing was not paradoxical but permitted by the laws of physics. The vacuum was pregnant with potential, and under conditions where that potential could be realized, universes could emerge. This did not answer all questions. Why do the laws of physics have the form they do? Why does the quantum vacuum have its particular properties? These remained open, but the shift from impossible to possible, from miraculous to natural, was significant. The origin of the universe moved from metaphysics into physics. The shift also changed how physicists thought about conservation laws. In the old paradigm, energy conservation seemed to forbid creation. How could energy appear from nothing? But in the new paradigm, the total energy of the universe might be zero, with positive energy from matter balanced by negative energy from gravity. Conservation was not violated but perfectly maintained. The paradigm shift was uncomfortable for many. It required abandoning intuitions built on everyday experience. Empty. Space in human experience really is empty. Removing objects from a room leaves nothing behind, but quantum mechanics operates at scales where intuition fails. The vacuum is not like an empty room, but like a quantum field in its lowest state, still active, still energetic. The shift also blurred boundaries. What distinguished something from nothing was no longer clear-cut. The vacuum was not matter, but it had energy. It was not particles, but it produced fluctuations. It was not being in the classical sense, but it had properties and dynamics. The line between existence and non-existence became fuzzy. This fuzziness was not a flaw in understanding, but a reflection of how nature actually works. The universe does not divide neatly into something and nothing. There are states, configurations, energy levels. The vacuum is one state, particles are excitations of that state, and the transition between them is continuous rather than discrete. The paradigm shift also highlighted the importance of quantum mechanics. In classical physics, nothing could be genuinely empty, but quantum mechanics introduced uncertainty, allowing fluctuations that made the vacuum active. Without quantum mechanics, the new understanding of the vacuum would not have been possible. This showed how different branches of physics were interconnected. Quantum field theory provided the framework for understanding the vacuum. General relativity showed how vacuum energy affected cosmic expansion. Particle physics tested vacuum properties through precision measurements. Cosmology observed vacuum effects on the largest scales. Each discipline contributed to the paradigm shift. As you rest completely now, let this shift settle gently. The paradigm is not fixed forever, but evolves as understanding deepens. What once seemed certain gives way to new insights. The vacuum is not empty, and this recognition transforms how we think about nothing, something, and the origin of everything. The shift is not complete. Questions remain, but the direction is clear, toward a universe where nothing and something are aspects of a deeper reality, where creation is natural rather than miraculous, where the quantum vacuum is the ground of existence. When the paradigm shift occurred, when physicists recognized that the vacuum was not empty but filled with fields and fluctuations, the effects rippled outward through multiple branches of science. These were not just abstract changes in how theorists thought, but practical shifts in how experiments were designed, how observations were interpreted, and how different fields of physics connected to one another. The immediate ripple was felt first in particle physics. If the vacuum was filled with fluctuating fields, then every measurement of particle properties had to account for vacuum effects. Calculations of masses, charges, and interaction strengths needed to include contributions from virtual particles, the temporary excitations of the vacuum that appeared and disappeared during interactions. This led to the development of sophisticated calculational techniques. Feynman diagrams, invented by Richard Feynman as a visual tool for tracking particle interactions, had to include loops representing virtual particles. Each loop added corrections to the basic process, and physicists learned to calculate these corrections with extraordinary precision. The result was a predictive framework of unprecedented accuracy. Quantum electrodynamics, the theory of how electrons and photons interact, could predict the magnetic moment of the electron to better than 1 part in a trillion, and experiments confirmed these predictions. This agreement depended critically on understanding vacuum fluctuations. Without accounting for the activity of the vacuum, theory and experiment would not match. The ripple extended to how experiments were designed. High-energy particle colliders were built not just to create new particles, but to probe the structure of the vacuum at small distance scales. By smashing particles together at extreme energies, physicists could temporarily create conditions where the vacuum behaved differently, revealing its underlying structure. The discovery of the Higgs boson in 2012 was a direct consequence of this approach. The Higgs field permeates the vacuum, and detecting its associated particle required understanding how the vacuum responded to high-energy disturbances. The success of the Large Hadron Collider demonstrated that vacuum physics was not theoretical speculation, but experimentally accessible reality. The immediate ripple also affected cosmology. If the vacuum had energy, as quantum field theory predicted, then it contributed to the expansion of the universe. Cosmologists had to include vacuum energy in their models, treating it as another component alongside matter and radiation. The discovery of accelerated expansion in 1998 confirmed this. Dark energy, most likely vacuum, energy, dominated the energy budget of the universe. Models of cosmic evolution had to be revised. The ultimate fate of the universe changed from potential recollapse to eternal expansion, driven by the repulsive effect of vacuum energy. This connection between quantum field theory and cosmology was profound. Phenomena occurring at the smallest scales, quantum fluctuations in the vacuum, affected the universe at the largest scales. The immediate ripple showed that physics was unified, that seemingly disparate fields were connected through the vacuum. Another area affected was astrophysics, understanding stellar evolution. Supernova explosions and black hole physics required accurate knowledge of particle interactions. Since those interactions involved vacuum effects, astrophysical models had to incorporate quantum field theory insights. Neutrino physics, crucial for understanding the sun and supernova, depended on vacuum properties affecting neutrino masses and mixing. The ripple extended to technology as well. Precision measurements of time and frequency, essential for GPS satellites and telecommunications, required understanding how electromagnetic fields behaved in the vacuum. Quantum effects that seemed purely academic had practical consequences for devices used daily. In atomic physics, understanding vacuum fluctuations improved calculations of atomic spectra. This had applications in developing atomic clocks, the most precise timekeeping devices available. These clocks, in turn, enabled tests of general relativity and searches for tiny variations in fundamental constants. The immediate ripple also affected how physics was taught. Textbooks had to be rewritten to include vacuum physics as a central topic rather than an advanced specialty. Students learned that empty space was not empty, that fields permeated everything, and that quantum fluctuations were not mathematical tricks but physical phenomena. This pedagogical shift changed how new physicists thought about the world. Instead of starting with particles and adding fields as secondary tools, they learned to think in terms of fields first, with particles as excitations. This inversion prepared them for the modern paradigm, where the vacuum was the foundation and everything else emerged from it. The ripple affected philosophy of science as well. If most of the universe was invisible, if the vacuum had properties that defied direct observation, then what did it mean to have empirical knowledge? Science had always relied on observation, but now much of reality was accessible only through indirect effects and theoretical inference. Philosophers debated whether dark matter and vacuum energy were real in the same sense that atoms and planets were real. Could entities known only through their effects be considered truly existent? Or were they merely useful fictions for organizing observations? Physicists largely dismissed these debates, confident that anything with measurable effects was real enough. But the questions highlighted how the paradigm shift challenged traditional empiricism. Reality extended beyond what could be directly observed, and science adapted by developing more sophisticated ways of inferring the unobservable from the observable. The immediate ripple also affected funding and research priorities. Governments and agencies invested in particle accelerators to probe vacuum structure. Satellites were built to map cosmic microwave background fluctuations. Underground laboratories searched for dark matter. Each project required substantial resources, justified by the paradigm shift that made vacuum physics central rather than peripheral. International collaborations formed to tackle questions too large for single institutions. The Large Hadron Collider involved thousands of physicists from dozens of countries. Satellite missions like Planck combined expertise from multiple nations. The ripple effects of the paradigm shift created a more interconnected, global scientific community. Another area affected was the search for physics beyond the standard model. If the vacuum had unexpected properties, perhaps there were new fields, new particles, or new symmetries waiting to be discovered. Theoretical frameworks like supersymmetry, string theory, and extra dimensions were motivated partly by trying to understand the vacuum at a deeper level. While these speculative theories had not yet been confirmed, the paradigm shift made them worth pursuing. If the vacuum we thought was empty turned out to be full, perhaps other surprises awaited at higher energies or smaller scales. The immediate ripple encouraged exploration beyond established boundaries. The shift also affected how scientists communicated with the public. Explaining that empty space was not empty required careful use of language and analogies. Science communicators developed new ways to convey quantum field theory concepts without overwhelming non-specialists. Documentaries, books, and articles explained vacuum fluctuations, dark energy, and the quantum nature of reality to broader audiences. This public engagement mattered because the paradigm shift changed how everyone, not just physicists, should think about the universe. The common-sense notion of empty space as truly empty was wrong. Understanding this required rethinking intuitions built on everyday experience. As you breathe slowly now, deeply relaxed, let the ripple effects settle. The paradigm shift was not an isolated event, but a transformation that spread through physics, technology, philosophy, and culture. Each ripple carried the insight that nothing is not empty, that the vacuum is the foundation of existence, and that understanding the universe requires recognizing the activity hidden within apparent emptiness. The immediate effects continue to unfold, shaping research, inspiring questions, and guiding the search for deeper truth. While the immediate effects of the paradigm shift rippled through contemporary physics, the longer-term consequences reverberated through the decades, reshaping entire fields and fundamentally altering humanity's understanding of existence, origins, and the nature of reality itself. These echoes through time showed that the shift was not merely technical, but philosophical. Not just about particles and fields, but about what it means for anything to exist at all. One of the deepest echoes was in how cosmologists approached the question of origins. Before the paradigm shift, the Big Bang singularity seemed like an impenetrable barrier, a point where physics broke down and science could say nothing. The singularity represented not just extreme conditions, but the apparent end of explanation, the place where natural law gave way to mystery or miracle. After the paradigm shift, this changed. The quantum vacuum provided a framework for thinking about what might have preceded or replaced the singularity. If the vacuum was not nothing, but a state with properties and dynamics, then asking how the universe emerged from the vacuum was a scientific question, not a philosophical dead end. Inflation theory, developed in the 1980s, embodied this new approach. It proposed that a quantum field in the early universe could drive exponential expansion, stretching a tiny region to cosmic scales. This inflation generated matter and energy from the vacuum energy of the field, creating the hot, dense state from which the standard Big Bang evolution proceeded. Inflation did not eliminate all mysteries. It did not explain why the field existed or why it had the properties it did, but it showed that the transition from a near-vacuum state to a universe filled with matter was not miraculous, but could follow naturally from quantum field theory and general relativity. The echoes of this insight continued to reverberate. By the early 21st century, inflation had become the standard framework for understanding the earliest moments. Observations of the cosmic microwave background confirmed its predictions. The patterns of temperature fluctuations matched what inflation expected, providing strong evidence that the universe did indeed undergo rapid expansion driven by a quantum field. This confirmation had profound implications. It meant that the largest structures in the universe, galaxies and galaxy clusters, originated from quantum fluctuations in the vacuum. The seeds of cosmic structure were fundamentally quantum, stretched from microscopic to macroscopic scales by inflation. The universe we observe arose from the activity of the vacuum, not from something imposed from outside. Another echo through time affected how physicists thought about the vacuum itself. The cosmological constant problem, the huge discrepancy between predicted and observed vacuum energy, remained unsolved decades after being recognized. This suggested that something fundamental was missing from our understanding. That the vacuum had properties or structure we had not yet grasped. Some physicists proposed that the vacuum might not be unique, that there could be many possible vacuum states, each with different properties. In string theory, the landscape of possible vacua might contain 10 to the 500 or more distinct states, each representing a different configuration of fields and forces. If this was correct, then our observable universe might occupy just one vacuum among countless others. The anthropic principle suggested that we necessarily find ourselves in a vacuum compatible with complex structures and observers, since universes with very different vacuum energies might not permit galaxies, stars, or life. This idea of a multiverse, with different regions having different vacuum properties, was controversial. Critics argued it was unfalsifiable, that it abandoned the traditional scientific goal of explaining why the universe is as it is. Defenders argued it was a natural consequence of inflation and quantum mechanics, that eternal inflation could produce bubble universes with different properties. Regardless of whether the multiverse idea is correct, its emergence showed how the paradigm shift continued to generate new frameworks decades later. The vacuum was not just one thing, but potentially many things, and this multiplicity opened new ways of thinking about cosmic diversity and the apparent fine-tuning of physical constants. The echoes also affected fundamental physics. The search for quantum gravity, a theory unifying general relativity and quantum mechanics, was motivated partly by trying to understand what the vacuum is at the Planck scale. String theory, loop quantum gravity, and other approaches all offered pictures of the vacuum as emerging from more fundamental structures, whether strings, loops, or something else. These theories were speculative, not yet confirmed by experiment, but they showed that the paradigm shift had opened questions that would take generations to answer. Understanding the vacuum completely might require revolutionary new physics. Theories as different from quantum field theory as quantum mechanics was from classical physics. Another long-term echo was in how the vacuum shaped technological development. Quantum technologies, including quantum computers and quantum communication, relied on manipulating quantum states and understanding vacuum fluctuations. Engineering the vacuum, controlling its properties in cavities and circuits, became a practical skill rather than purely theoretical exercise. Cavity quantum electrodynamics, the study of how atoms interact with electromagnetic fields in confined spaces, showed that vacuum properties could be modified by boundary conditions. This had applications in building better detectors, improving quantum information processing, and developing new materials with exotic properties. The echoes extended to philosophy and culture, the recognition that most of reality was invisible, that the vacuum was not empty, challenged materialist philosophies based on the primacy of observable matter. If the universe was dominated by dark matter, dark energy, and vacuum fields, all unobservable directly, then what counted as real? Some philosophers argued this showed the limits of naturalism, that science was appealing to increasingly abstract and unobservable entities. Others argued it demonstrated the power of science to transcend direct observation, to infer the unobservable from its effects, and to build knowledge through mathematics and indirect evidence. The cultural echoes included changes in how people thought about existence and nothingness. The ancient question of why there is something rather than nothing took on new dimensions. Science could not answer the question completely, could not explain why the laws of physics exist, but it could show that given those laws, the emergence of something from the quantum vacuum was natural rather than miraculous. Religious thinkers engaged with these ideas in various ways. Some saw the Big Bang and the apparent beginning of time as consistent with creation narratives. Others argued that the quantum vacuum was not true nothingness, and that the question of ultimate origins remained unanswered. Still others welcomed the dialogue between science and theology, seeing complementary rather than contradictory approaches to existence. The echoes through time also included educational transformation. By the 21st century, students learned about vacuum physics, dark energy, and cosmic inflation as standard topics. What had once been cutting-edge research became foundational knowledge, preparing new generations to push further into the unknown. This accumulation of knowledge showed how science progresses. Each generation builds on the previous, extending the paradigm, testing its limits, proposing refinements. The paradigm shift of recognizing that the vacuum is not empty did not end investigation, but opened new avenues, new questions, new frontiers. The echoes also revealed how science interfaces with uncertainty. Despite tremendous progress, fundamental questions remained. What is dark matter? What is dark energy? How did inflation begin? What is the vacuum at the Planck scale? These open questions were not failures but invitations, signs that the paradigm shift had revealed new mysteries as it resolved old ones. As you rest completely now, breathing gently, let these echoes through time bring perspective. The paradigm shift continues to reverberate, shaping research decades later, inspiring new theories, guiding observations. The recognition that nothing is not empty transformed physics, but the transformation is ongoing. Each generation adds to understanding, echoing forward in time, building toward a fuller grasp of why the universe exists and how it emerged from the quantum vacuum. Behind every equation describing the quantum vacuum, behind every observation of cosmic expansion, behind every theory proposing how the universe could arise from nothing, there were people. Individuals who looked at the universe and refused to accept that its origins were beyond understanding, who pursued ideas that seemed impossible, who dedicated years or decades to questions that had no guaranteed answers. Think of Alexander Friedman, working in Russia in the early 1920s, solving Einstein's equations without the artificial cosmological constant. He found solutions describing expanding and contracting universes, publishing them in obscure journals that few people read. His work was mathematical exploration, not observational cosmology. He was asking what the equations allowed, not what the universe actually did, but he showed that general relativity naturally predicted dynamic cosmologies, planting seeds that would grow decades later. Friedman died young in 1925 at age 37, never seeing his solutions become the foundation of modern cosmology. But his willingness to follow the mathematics wherever it led, even to conclusions that contradicted prevailing assumptions, exemplified the spirit of those who pursued cosmic origins. Consider Georges Lemaitre, the Belgian priest and physicist who proposed the primeval atom. He combined mathematical sophistication with philosophical daring, suggesting that the universe had a beginning, that time itself emerged from a singular state. This was not merely a scientific proposal, but a profound rethinking of existence, causality, and the nature of reality. Lemaitre faced skepticism from colleagues who found the idea of a cosmic beginning religiously motivated or scientifically suspect, but he insisted on separating his scientific work from his theological beliefs, arguing that physics could describe how the universe evolved without addressing ultimate why questions. His patience and rigor eventually convinced others that the expanding universe was real, and that tracing it backward led to a beginning. Think of Fred Hoyle, who coined the term Big Bang dismissively during a radio broadcast, yet whose own steady-state theory, proposing continuous creation of matter rather than a singular beginning, pushed cosmology forward by forcing proponents of the Big Bang to sharpen their arguments and predictions. Even those who opposed the emerging consensus contributed by demanding better evidence and clearer explanations. Consider Alan Guth, developing inflation theory in the late 1970s. He was trying to solve technical problems in particle physics, puzzles about why certain predicted particles were not observed, when he realized that a brief period of exponential expansion in the early universe could solve multiple cosmological problems simultaneously. The horizon problem, the flatness problem, the absence of magnetic monopoles, all could be explained if the universe underwent rapid inflation driven by a quantum field. Guth's proposal was bold. It required accepting that quantum field dynamics could drive cosmic expansion, that vacuum energy could inflate space, that the entire observable universe arose from a region smaller than a proton. Many physicists initially dismissed it as too speculative, but as the theory was refined by Guth, Andre Linde, Paul Steinhardt, and others, it became clear that inflation solved too many problems to be coincidence. The dreamers were not just theorists. Observers played crucial roles. Edwin Hubble, whose careful measurements revealed that galaxies were receding, provided the first evidence for cosmic expansion. His work required painstaking observation, nights at the telescope, careful calibration of instruments, and meticulous analysis of photographic plates. The discovery was built on technical skill as much as insight. Vera Rubin, measuring rotation curves of galaxies and discovering evidence for dark matter, faced skepticism about her results and discrimination as a woman in a male-dominated field. But she persisted, accumulating data that could not be ignored, showing that the universe contained far more than met the eye. Her determination opened the door to understanding that most of reality is invisible. Think of the teams measuring distant supernovae in the 1990s, expecting to find that cosmic expansion was slowing but discovering instead that it was accelerating. Saul Perlmutter, Brian Schmidt, Adam Rees, and their collaborators followed the data even when it contradicted expectations, revealing that dark energy dominates the universe. Their willingness to trust observations over intuition exemplified scientific integrity. Consider Stephen Hawking, proposing with James Hartle that the universe has no boundary in time, that asking what came before the Big Bang is like asking what is south of the South Pole. This required thinking about time itself as emergent, not fundamental, and applying quantum mechanics to the universe as a whole. The mathematics was difficult, the concepts abstract, but the framework offered a way to address origins without invoking singularities or external causes. The dreamers also included those working on quantum gravity. Pioneers of string theory like Michael Green, John Schwartz, and others pursued the idea that fundamental objects were not points but extended strings, despite decades when the theory seemed untestable and unfashionable. They believed that unifying quantum mechanics and gravity required revolutionary new physics, and they worked toward that goal even when the path was unclear. Loop quantum gravity researchers like Abhay Ashtekar, Carlo Rovelli, and Lee Smolin took a different approach, quantizing space-time itself, proposing that space has a granular structure at the Planck scale. Their vision of a quantum bounce replacing the Big Bang singularity offered another way to think about cosmic origins, showing that multiple paths toward understanding were being explored simultaneously. Think of the experimentalists building particle accelerators, satellite observatories, and underground detectors. The Large Hadron Collider required decades of planning, billions of dollars, and collaboration among thousands of physicists. Its discovery of the Higgs boson confirmed that the vacuum is structured by a field that gives particles mass, a crucial piece of understanding what empty space actually is. Satellite missions like COBE, WMAP, and Planck mapped the cosmic microwave background with increasing precision, revealing the tiny fluctuations that grew into galaxies. Each mission required engineering sophisticated instruments, launching them into space, collecting data over years, and analyzing billions of measurements. The dedication of scientists and engineers made these observations possible. Consider also the graduate students, postdocs, and junior researchers who did much of the actual work, following leads that senior scientists proposed, performing calculations, analyzing data, running simulations. Many of their names are not famous, but their contributions were essential. Science advances through collective effort, each person adding pieces to a larger puzzle. The dreamers were motivated by different things. Some sought fame and recognition, others were driven by pure curiosity, wanting to understand for its own sake. Many found beauty in the mathematics, elegance in the theories, satisfaction in solving problems that had seemed intractable. Some saw their work as part of a larger human quest to understand existence. What united them was willingness to pursue difficult questions, to challenge established ideas, to follow evidence and logic, even to uncomfortable conclusions. They worked in different countries, different eras, different subfields, but together they built the framework through which we now understand cosmic origins. The dreamers also faced setbacks. Theories that seemed promising failed experimental tests. Observations contradicted predictions. Careers were spent on ideas that turned out to be wrong. But even failed theories contributed by ruling out possibilities, by sharpening questions, by showing what the universe is not. Think of the conferences where ideas were debated, the papers where new frameworks were proposed, the collaborations where different expertise combined. Science is a social enterprise, built through communication and critique, through sharing data and methods, through arguing and eventually reaching consensus when evidence becomes overwhelming. The dreamers included philosophers and mathematicians who contributed conceptual tools even if they did not perform experiments. The philosophical question of whether something could come from nothing had been debated for millennia. Physicists brought it into the domain of science, but philosophers helped clarify what was being asked and what kinds of answers were possible. Mathematicians developed the tools needed for general relativity, quantum field theory, and string theory. Without differential geometry, without group theory, without the techniques for handling infinite dimensional spaces, the physics could not have been formulated. The dreamers included those who built the mathematical infrastructure. As you breathe slowly now, completely relaxed, think of these dreamers scattered across time and space. From Friedman in the 1920s to researchers today, each contributed to understanding whether and how the universe could arise from nothing. Their collective effort, spanning a century, transformed the question from philosophy to science, from speculation to testable theory. They showed that the deepest mysteries could be approached with patience, rigor, and imagination. They were dreamers who made their dreams into knowledge. For every bold claim about cosmic origins, for every proposal that the universe could arise from quantum fluctuations in the vacuum, there were skeptics who questioned the evidence, challenged the logic, and demanded better explanations. This opposition was not obstruction, but an essential part of how science works. Truth emerges not from consensus, but from the grinding process of claim and counterclaim, from testing ideas until only those that can withstand scrutiny remain standing. When Einstein first published general relativity, not everyone accepted it immediately. Despite its mathematical elegance and its explanation of Mercury's orbit, some physicists remained unconvinced. They proposed alternative theories, questioned whether the bending of light during eclipses really proved relativity, and argued that simpler explanations might exist. This skepticism was healthy. Extraordinary claims require extraordinary evidence. A complete reformulation of gravity and space-time demanded thorough testing. The confirmation of light bending in 1919 provided crucial support, but even then, some remained cautious. Only as more predictions were confirmed, as relativity explained phenomena that other theories could not, did it achieve widespread acceptance. When Hubble presented evidence for cosmic expansion, skeptics questioned whether redshifts really indicated motion. Perhaps some unknown physical process stretched light without requiring galaxies to recede. Perhaps instruments were systematically biased. Perhaps the interpretation was wrong, and the universe remained static after all. Steady-state theory, developed in the 1940s by Fred Hoyle, Hermann Bondi, and Thomas Gold, offered an alternative to the Big Bang. It proposed that the universe had no beginning, that it looked the same at all times, and that new matter continuously formed to maintain constant density as space expanded. This theory was motivated partly by philosophical discomfort with the idea of a cosmic beginning. The battle between Big Bang and steady-state cosmology lasted decades. Each side made predictions, and observations gradually favoured the Big Bang. The discovery of the cosmic microwave background in 1965 was decisive. Steady-state theory had no natural explanation for this uniform radiation filling the universe, while the Big Bang predicted it as a relic of a hot, dense past. Even then, proponents of steady-state tried to save the theory by adding mechanisms to explain the background. But the modifications became increasingly contrived. Eventually, the weight of evidence became overwhelming, and steady-state theory was abandoned by all but a few holdouts. The battle taught important lessons. Alternative theories, even if ultimately wrong, forced Big Bang proponents to sharpen their arguments, make precise predictions, and account for all observations. The criticism made the Big Bang framework stronger by requiring it to pass every test. When inflation was proposed in the 1980s, skeptics immediately questioned whether it was necessary. Perhaps the horizon and flatness problems could be solved without invoking exponential expansion. Perhaps the theory was too flexible, capable of explaining anything, and therefore explaining nothing. Perhaps it was untestable speculation rather than genuine science. These criticisms pushed inflation theorists to make specific predictions that observations could test. Inflation predicted a nearly scale-invariant spectrum of fluctuations, with slight deviations characterized by measurable parameters. It predicted that the universe should be flat. It predicted no large-scale variations in the cosmic microwave background beyond those from inflation's quantum seeds. Observations confirmed these predictions. The cosmic microwave background showed precisely the patterns inflation expected. The universe was measured to be flat within observational uncertainties. The spectrum of fluctuations matched inflation's framework. These successes did not silence all critics, but they established inflation as the leading explanation for cosmic origins. The discovery of dark energy in 1998 faced immediate skepticism. The supernova measurements seemed to show accelerating expansion, but were there systematic errors? Were distant supernovae dimmer because of dust absorption rather than distance? Were assumptions about supernova uniformity incorrect? Multiple teams independently confirmed the result using different supernovae and different analysis methods. The cosmic microwave background provided independent evidence for dark energy. Galaxy clustering showed the same pattern. The convergence of evidence from multiple sources overcame initial skepticism, though questions about the nature of dark energy remained. The cosmological constant problem, the huge discrepancy between predicted and observed vacuum energy, led some physicists to question whether vacuum energy was real at all. Perhaps dark energy was something else entirely, not related to quantum fluctuations. Perhaps modifications to general relativity at large scales could explain acceleration without requiring vacuum energy. These alternatives were explored seriously. Modified gravity theories were proposed and tested against observations. So far, none fit the data as well as vacuum energy within general relativity. But the search continued because the cosmological constant problem remained unsolved. The battle for truth also involved debates about what counted as explanation. When physicists proposed that the universe could arise from quantum fluctuations in the vacuum, critics objected that this was not really something from nothing. The vacuum had properties, had fields, had energy. It was not philosophical nothingness, but a state with structure. Defenders responded that philosophical nothingness was not a scientific concept, that physics could only describe states obeying physical laws, and that the vacuum was the closest thing to nothing that physics recognized. The debate highlighted different standards for what counted as explanation. Some philosophers argued that physics had not solved the problem of origins, merely pushed it back one step. Instead of asking why the universe exists, we now ask why the quantum vacuum exists. Instead of asking where matter came from, we ask where the vacuum energy came from. The ultimate why question remained unanswered. Physicists largely agreed that ultimate why questions might lie outside science, but argued that showing how the universe could arise naturally from the vacuum was significant progress. It demonstrated that origins were not miraculous, that they followed from laws we could write and test, that they were part of nature rather than beyond it. The battle also involved technical disputes. Different methods for calculating vacuum energy gave different results. Different interpretations of quantum field theory led to different predictions. Different approaches to quantum gravity offered different pictures of what happened at the Planck scale. These disputes were resolved not through authority, but through careful comparison with observations. Sometimes the battles became personal. Scientists are human, with egos and ambitions. Credit for discoveries was sometimes disputed. Competing research groups rushed to publish first. Conferences saw heated exchanges, but the scientific method provided mechanisms for resolving disputes. Repeated observations, independent confirmation, and mathematical rigor ensured that personal conflicts did not derail the search for truth. The opposition also came from those uncomfortable with the philosophical implications. If the universe arose from nothing, did that make existence meaningless? If origins were purely physical, what room remained for purpose or significance? These concerns, while not scientific objections, influenced how some people responded to the theories. Religious thinkers had mixed reactions. Some saw the Big Bang as consistent with creation narratives, while others worried that naturalizing origins eliminated the need for a creator. Some welcomed the dialogue between science and theology, seeing complementary perspectives on existence. Others insisted on maintaining separation between the two domains. The battle for truth showed that science progresses through conflict as much as cooperation. Ideas that survive criticism become stronger. Theories that fail under scrutiny are discarded. The process is messy, sometimes slow, occasionally contentious. But it works. What emerges is not certainty but justified confidence, knowledge that has been tested and has held up. The opposition served crucial functions. It prevented premature acceptance of ideas that seemed appealing but lacked solid support. It demanded precision in claims and rigor in arguments. It ensured that evidence, not authority or eloquence, determined what was accepted as true. As you rest deeply now, let the battle for truth bring calm rather than anxiety. Conflict in science is not destructive, but productive. Skepticism is not opposition to knowledge, but its guardian. Questions are not threats, but invitations to deepen understanding. The battle for truth continues, as it should, ensuring that what we believe is grounded in observation, tested by logic, and refined by criticism. The truth that emerges is stronger for having been challenged. There comes a point in understanding when abstract physics transforms into personal comprehension, when equations and theories cease to be mere intellectual constructs and become ways of seeing the world differently. This is the new awareness that emerges from grappling with the question of whether the universe came from nothing, a shift not just in what we know, but in how we experience existence itself. The awareness begins with scale. We are used to thinking of ourselves as substantial, of the earth as solid, of the physical world as the primary reality. But the quantum vacuum, the dark matter, the dark energy, all of these remind us that what we perceive directly is a tiny fraction of what exists. The solid ground beneath us is mostly empty space between atoms. The atoms themselves are excitations of quantum fields. The vacuum surrounding everything is not empty but seething with activity. This realization can be unsettling. If most of reality is invisible and intangible, if what we call nothing is actually something, if the universe we inhabit is dominated by components we cannot see or touch, then what does it mean to know the world? Our senses evolved to navigate a macroscopic environment. They tell us nothing about quantum fields or dark matter. Yet these unseen components shape everything we experience. The new awareness involves accepting that direct perception is limited, that knowledge extends far beyond what senses reveal. Science provides tools, mathematics and instruments and reasoning that allow us to infer the unobservable from the observable, to understand what we cannot directly experience. This is both humbling and empowering. Humbling because it shows how partial our intuitive grasp is. Empowering because it demonstrates that we can transcend those limitations through thought and investigation. Another dimension of the new awareness involves time. We are used to thinking of time as flowing steadily from past to future, as an absolute background against which events occur. But general relativity showed that time is relative, that it flows at different rates depending on motion and gravity. Near the Big Bang, in conditions of extreme density and energy, the concept of time itself may break down or transform. The no-boundary proposal suggests that time near the origin becomes like space, that asking what happened before the Big Bang is incoherent, like asking what is south of the South Pole. This requires thinking about time not as fundamental but as emergent, not as container, but as aspect of space-time geometry. The awareness is that time itself has a structure and history, that it is not eternal or absolute, but part of the dynamic unfolding of the universe. The new awareness also touches causality. We are deeply conditioned to think in terms of cause and effect, to assume that every event has a prior cause, that the chain of causality extends backward indefinitely. But quantum mechanics introduces fundamental randomness. Events occur without deterministic causes, only probabilities. And at the cosmic scale, causality itself might not extend beyond the Big Bang. This does not mean the universe is arbitrary or chaotic. It means that causality, like time, may be emergent rather than fundamental. At the quantum level, events occur according to probabilities, determined by wave functions. The universe as a whole might not have a cause in the traditional sense, but might arise from quantum processes where probability replaces deterministic causation. Accepting this requires a shift in how we think about explanation. We seek reasons why things happen, but at the deepest level, the answer might be that they happen because quantum mechanics permits them with certain probabilities. This is less satisfying than traditional causal stories, but may be closer to how nature actually works. The awareness extends to existence itself. Why is there something rather than nothing? Physics cannot answer this completely, cannot explain why the laws of physics exist, or why the quantum vacuum has the properties it does. But it can show that given those laws and properties, the emergence of the universe is natural rather than miraculous, permitted rather than prohibited, probable under certain conditions rather than inexplicable. This shifts the question without fully answering it. Instead of a single profound mystery, there are layers. The emergence of the universe from the vacuum can be explained. The existence of the vacuum and its properties cannot, at least not yet. Perhaps deeper theories will address those questions. Perhaps they will remain forever, outside science. Either way, the awareness is that some mysteries may be irreducible, that the search for understanding has limits we have not yet reached. The new awareness also involves recognizing our place in this vast story. We are not outside observers looking at the universe from a privileged position. We are part of the universe, made of the same quantum fields, shaped by the same vacuum properties, products of the same evolutionary processes that began with quantum fluctuations stretched by inflation. The atoms in our bodies were forged in stars. The patterns of our neurons arose from physical laws. Consciousness itself, mysterious as it is, operates within the physical universe. This does not diminish human significance. If anything, it deepens wonder. We are arrangements of quantum fields complex enough to contemplate the quantum vacuum. We are matter organized to understand its own origins. We are the universe becoming aware of itself. The awareness also brings perspective on meaning and purpose. If the universe arose from quantum processes, if its structure is explained by physical law, does that make existence meaningless? Or does meaning arise not from external imposition but from internal creation, from the fact that conscious beings can value, love, create, and understand? Science describes how things are. It does not prescribe how they should be or what they mean. The awareness is that physics and meaning occupy different domains, that understanding cosmic origins does not resolve questions of purpose but clarifies them, showing that purpose is something we construct rather than something imposed from outside. Another aspect of the awareness involves uncertainty. Despite tremendous progress, fundamental questions remain unanswered. What is dark matter? What is dark energy? How did inflation begin? What is the vacuum at the Planck scale? These open questions are not failures but invitations. They show that understanding is incomplete, that the search continues, that each answer reveals new mysteries. Living with uncertainty is part of the new awareness. We want definitive answers, complete explanations, final truths, but science proceeds through approximation and refinement. What we know now is better than what we knew before, but will be superseded by what we learn next. The awareness is that knowledge is provisional, always subject to revision, yet still genuine and useful. The awareness also includes recognizing the achievement of understanding, that humans on one small planet could discover quantum mechanics, formulate general relativity, observe cosmic expansion, detect the microwave background, propose inflation, and show how the universe might arise from the quantum vacuum is itself remarkable. The universe is comprehensible. That fact is as profound as any particular discovery. As you breathe deeply now, completely at rest, let this new awareness settle gently. You exist in a universe that arose from quantum fluctuations, expanded from a hot, dense state, filled with invisible matter and energy, dominated by a quantum vacuum that is not empty. This is not alienating, but connecting. You are part of the story, made of its substance, shaped by its history. The awareness changes not what you are, but how you understand what you are, linking the personal to the cosmic, the immediate to the eternal, the self to the vast fabric of existence from which everything emerged. After exploring theories, data, and implications, after following the journey from philosophical speculation to scientific investigation, we arrive at what might be called the deepest truth that physics has revealed about the question of whether the universe came from nothing. This truth is not a simple answer, but a framework, a way of understanding that transforms the question itself. The deepest truth is this: the universe as a whole may have a total energy of exactly zero, and if so, its existence violates no conservation laws. Creation from nothing is not forbidden by physics, but permitted by it. The apparent miracle of something arising from nothing dissolves when we recognize that the something and the nothing balance perfectly. To understand this, recall that energy in physics comes in different forms. Matter has positive energy, related to mass through Einstein's equation. Radiation carries positive energy. Kinetic energy, the energy of motion, is positive. All of these contribute to what we think of as the stuff of the universe, the content that makes existence substantial. But gravity contributes negative energy. When masses attract, their gravitational potential energy is negative. This is not arbitrary, but follows from how potential energy is defined in physics. We set the 0 point at infinite separation, where gravitational influence vanishes. As masses come closer, their potential energy decreases, becoming more negative. For bound systems like the Earth and Moon, or the Solar System, or galaxies, the total energy, kinetic plus gravitational potential, is negative. The system is bound, unable to escape to infinite separation without additional energy input. This is familiar physics, confirmed by every orbit and every trajectory. Applied to the universe as a whole, this principle suggests something remarkable. If the positive energy of all matter and radiation exactly balances the negative gravitational potential energy of the universe, pulling on itself, then the total energy is zero. The universe does not cost anything to exist. Its energy budget is perfectly balanced. This is not just speculation. Observations suggest the universe is spatially flat, meaning its density is at the critical value where expansion will continue forever, gradually slowing but never reversing. Flatness corresponds to zero total energy. The universe sits precisely at the boundary between expansion and collapse, and that boundary is where the energy adds to zero. Inflation provides a mechanism for why the universe is flat. During the exponential expansion, any initial curvature was stretched until the observable universe became effectively flat, and inflation naturally produces a zero-energy universe, because the positive energy generated in matter and radiation is exactly balanced by the negative gravitational energy of the expanding space. Alan Guth emphasized this balance. Inflation creates enormous amounts of matter and radiation, filling the universe with particles and fields, but it simultaneously creates an equal amount of negative gravitational potential energy. The books balance. Conservation of energy is not violated because the total remains zero throughout. This realization changes how we think about cosmic origins. Instead of asking where the energy came from to make the universe, we recognize that no net energy was needed. The universe is a vast rearrangement of zero, positive and negative contributions cancelling exactly. From the perspective of energy accounting, the universe is nothing, even though it contains everything. The deepest truth extends to other conservation laws. Momentum conservation is maintained because the universe has no preferred direction. Every particle moving one way is balanced by particles or gravitational effects going the other way. Angular momentum, electric charge, and other quantities also sum to zero when the universe is considered as a whole. This means the universe could arise from a quantum fluctuation in the vacuum without violating any conservation law. Fluctuations are permitted by the uncertainty principle, which allows energy to be borrowed temporarily. But if the total energy is zero, then nothing is borrowed. The fluctuation costs nothing because it creates equal amounts of positive and negative contributions. Lawrence Krauss, in his book on this topic, argued that this constitutes an explanation for how the universe can come from nothing within the framework of physics. Critics responded that the quantum vacuum is not nothing, that it has properties and structure, that the laws of physics themselves are something that requires explanation. Both perspectives have merit. From the physics perspective, the quantum vacuum is the relevant nothing, the state with no particles and minimum energy. Showing that a universe can arise from this state without violating conservation is significant. It demonstrates that origins are not miraculous, that they follow from the laws we know, that creation is permitted by nature. From the philosophical perspective, the vacuum is not absolute nothingness. It is a state with properties, governed by laws, capable of fluctuating. Ultimate questions about why the laws exist or why anything exists at all remain unanswered. The deepest truth from physics does not eliminate philosophical mystery, but relocates it. What physics has achieved is showing that the intermediate steps, from vacuum to universe, from fluctuation to inflation, from quantum seeds to galaxies, all follow naturally without violating principles or requiring external intervention. The chain of explanation connects the vacuum state to the observed cosmos, through mechanisms that can be written mathematically and tested observationally. The zero-energy universe hypothesis also addresses the problem of initial conditions. If the total energy is zero, then the universe can begin from a state with no energy, no special setup, no fine-tuning required. The vacuum is the natural starting point, and the balance of energies ensures that evolution from that state is consistent with conservation. This connects to symmetry. Conservation laws arise from symmetries through Noether's theorem. Energy conservation follows from time translation symmetry, the fact that physical laws do not change over time. If the universe respects this symmetry, then energy is conserved, and if the total energy is zero, that value is conserved throughout all evolution. The deepest truth also illuminates why existence might be more natural than non-existence. If absolute philosophical nothing is unstable or undefined, if quantum mechanics requires fluctuations, if zero-energy configurations are permitted, then existence might be the default. Non-existence, absolute nothingness with no potential for anything, might be the unstable or impossible state. This inverts the traditional question. Instead of asking why there is something rather than nothing, we might ask whether nothing was ever a real option. Perhaps the quantum vacuum, with its fields and fluctuations, is the ground state of reality, and universes arise naturally from it. Perhaps existence is not surprising but inevitable. The deepest truth does not resolve all questions. Why do the laws of physics have the form they do? Why does quantum mechanics govern the vacuum? Why is there a universe-generating mechanism rather than none? These questions remain, possibly beyond science, possibly awaiting deeper theories. But what physics has accomplished is profound. It has shown that the boundary between nothing and something is not absolute, that conservation laws permit rather than forbid cosmic origins, that the energy of everything can sum to zero, and that the universe we observe is consistent with having emerged naturally from the quantum vacuum. The deepest truth is that creation is balanced, that existence does not violate the rules, that something from nothing is possible because the something is a rearrangement of nothing, positive and negative contributions in exquisite equilibrium. This is the framework within which physics addresses the ancient question, not a complete answer, but a profound insight into how nature operates at the deepest level. As you rest completely now, let this deepest truth settle without strain. The universe balances, existence is permitted, creation follows from conservation. The quantum vacuum is the source and the nothing from which everything emerged, is not empty void but structured potential. The deepest truth transforms mystery into mechanism, wonder into understanding, showing that the universe is both more comprehensible and more remarkable than traditional accounts suggest. After travelling through the physics of quantum vacuums, cosmic expansion, dark energy, and zero-energy universes, after understanding how science approaches the question of origins, we arrive at a place of reflection, not to close the inquiry, but to ponder what it all means, to ask not just how the universe began, but what that beginning says about existence, knowledge, and our place in the vastness. The first meaning that emerges is about the power and limits of science. Physics has shown that the universe could arise from the quantum vacuum, that conservation laws permit such origins, that mechanisms like inflation connect quantum fluctuations to cosmic structure. This is an extraordinary achievement, bringing a question that seemed purely philosophical into the realm of testable science. But science has not answered why the laws of physics exist, why the quantum vacuum has the properties it does, or why there is something rather than absolute philosophical nothing. These questions may lie beyond science, or they may await future theories we cannot yet imagine. The meaning is that science is powerful but not omnipotent, that it can illuminate vast territories of mystery without eliminating mystery entirely. Another meaning involves how we think about causality and origins. We are conditioned to ask what caused the universe, to seek a prior event or agent that brought it into being. But if time itself emerged with the universe, if quantum mechanics replaces deterministic causation with probability, if the universe arose from the vacuum not through causation but through quantum transition, then our causal intuitions may not apply. The meaning is that causality might be emergent rather than fundamental, applicable within the universe, but not necessarily to the universe as a whole. This does not make existence arbitrary, but suggests that at the deepest level, explanation takes different forms than we are used to. Probability, symmetry, and conservation may be more fundamental than cause and effect. Pondering the meaning also involves thinking about necessity and contingency. Could the universe have been different? Could the laws of physics have taken other forms? If the quantum vacuum can exist in multiple states, each corresponding to different physics, then perhaps our universe is one possibility among many, selected not by necessity but by chance or by anthropic reasoning. If so, then existence is contingent, not necessary. There is no single inevitable way the universe must be. This can feel unsettling, suggesting that everything is accidental, or it can feel liberating, showing that the universe is not rigidly determined but open, that possibility is woven into reality at the deepest level. The meaning for human significance is complex. On one hand, understanding that the universe arose from quantum processes, that its structure is explained by physical law, that consciousness emerged through natural selection, all of this seems to diminish human importance. We are not the purpose of creation, but products of impersonal processes operating over billions of years. On the other hand, the fact that matter can organize itself into forms capable of understanding quantum mechanics, contemplating cosmic origins, and asking profound questions is itself remarkable. We are, the universe, become conscious, structures of quantum fields arranged to comprehend the vacuum from which everything emerged. That capacity for understanding is as much a part of the universe as galaxies and stars. The meaning is that significance is not diminished by naturalistic explanation, but transformed. We are not less important because we arose through physical processes. We are more remarkable because those processes, operating blindly, generated beings capable of thought, love, creativity, and wonder. Pondering the meaning also involves thinking about the relationship between science and other ways of knowing. Science describes how the universe evolved, what its components are, what laws govern its behavior. But it does not address questions of value, purpose, or meaning in the existential sense. Those remain domains for philosophy, religion, art, and personal experience. The meaning is that understanding cosmic origins does not resolve all questions about existence. It clarifies some, showing that naturalistic explanations are possible, but it leaves others untouched, showing that science is one way of knowing among many, powerful within its domain but not exhaustive of human inquiry. Another aspect of meaning involves beauty and elegance. The fact that the universe might have zero total energy, that quantum fluctuations seed galaxies, that inflation solves multiple problems with a single mechanism. All of this exhibits a kind of aesthetic appeal. The theories are not just true but beautiful, exhibiting symmetry, simplicity, and explanatory power. This beauty is not mere decoration. It often guides physicists toward fruitful ideas, theories that are mathematically elegant, that unify disparate phenomena, that reveal unexpected connections, tend to be correct. Beauty is a clue to truth, suggesting that the universe at its deepest level has a structure that resonates with mathematical harmony. The meaning of this is debated. Some see it as evidence that the universe is intelligible because it was designed to be understood. Others see it as a selection effect, that we notice elegance because our minds evolved to recognize patterns. Still others see it as reflecting deep principles, that symmetry and simplicity are fundamental rather than accidental features of reality. Pondering the meaning also involves considering the future. If physics continues to progress, might we eventually understand why the laws exist, why the quantum vacuum has its properties, why there is something? Or will these questions remain forever outside science, part of an irreducible mystery at the heart of existence? The answer is uncertain, but the history of science suggests humility. Questions that seemed unanswerable became tractable as new tools and concepts developed. What now appears beyond science may yield to future theories, but even if ultimate questions remain unanswerable, the progress made in understanding intermediate layers, from vacuum to universe, is genuine and valuable. The meaning for how we live our lives is subtle but real. Knowing that the universe arose from quantum processes does not tell us how to act, what to value, or how to treat each other. But it provides context, showing that we are part of a vast story, connected to the deepest structures of reality, temporary but meaningful manifestations of matter's capacity to organize, think, and understand. This can inspire awe and gratitude, a sense of wonder at existence itself. It can also inspire humility, recognizing how much we do not know, how partial our understanding remains, how vast the universe is compared to our brief lives. Both responses are appropriate. The meaning also includes recognizing the collective nature of understanding. No single person discovered that the universe could arise from nothing. It required contributions from Einstein, Friedman, Lemaitre, Hubble, Rubin, Guth, Hawking, and countless others, each building on previous work, each adding pieces to a larger picture. Knowledge is communal, built through collaboration across generations and cultures. This suggests that meaning is also communal, that we participate in something larger than individual existence, that our understanding contributes to a collective human project of making sense of reality. This participation itself has value, connecting us to past and future, linking individual curiosity to universal questions. As you breathe slowly now, deeply relaxed, ponder these meanings without forcing conclusions. The question of whether the universe came from nothing opens into multiple meanings, some clear, some ambiguous, some personal, some universal. Physics provides frameworks and mechanisms but does not dictate how we interpret their significance. That interpretation is part of being human, part of how we make sense of existence and our place within it. We have travelled far through this long night, from the initial question of whether the universe came from nothing to explorations of quantum vacuums, cosmic expansion, inflation, dark matter, dark energy, and the zero-energy hypothesis. We have followed the history of ideas, the accumulation of evidence, the paradigm shifts that changed how physicists understand reality. Now, as our journey concludes, it is time to return to where we began, to the simple act of wondering, enriched by understanding. The legacy of the scientific investigation is profound. The question that philosophers debated for millennia has been partially addressed by physics. Not completely answered, for ultimate why questions may lie beyond science, but significantly illuminated. We now know that the quantum vacuum is not empty, that it has structure and energy, that it fluctuates according to quantum mechanics, and that these fluctuations can, under certain conditions, give rise to expanding universes. We know that conservation laws, far from forbidding creation, actually permit it if the total energy of the universe is zero. We know that inflation provides a mechanism for exponential expansion that stretches quantum seeds to cosmic scales. We know that the cosmic microwave background carries imprints of these quantum origins, testable predictions confirmed by observation. The legacy is that origins are not miraculous but natural, not violations of physical law but consequences of it. The universe we observe is consistent, with having emerged from the quantum vacuum through processes that physics can describe mathematically and test empirically. This is knowledge, genuine understanding built through decades of patient investigation, but the legacy also includes recognizing the limits of that knowledge. Physics describes how the universe could arise from the quantum vacuum. It does not explain why the vacuum exists, why the laws of physics have the form they do, or why there is something rather than absolute philosophical nothing. These questions remain, pointing toward deeper mysteries or perhaps toward the boundaries where science ends and philosophy begins. The legacy includes technological and practical consequences. Understanding vacuum fluctuations led to precision measurements that enabled GPS satellites and quantum technologies. Understanding cosmic expansion revealed that the universe's fate is eternal acceleration driven by dark energy. Understanding dark matter showed that most of reality is invisible, fundamentally changing how we map and model the cosmos. The legacy extends to how we teach and think. The paradigm shift from treating empty space as truly empty to recognizing it as a seething quantum foam has been incorporated into physics education. Students now learn quantum field theory as the foundation for particle physics, with the vacuum as the ground state from which everything emerges. This shapes how the next generation approaches reality. The legacy also includes inspiring wonder. The fact that the universe might have arisen from quantum fluctuations, that the vacuum is not nothing but something, that existence balances positive and negative energies in perfect equilibrium, all of this is as awe-inspiring as any traditional creation story. Science has not diminished wonder but deepened it, showing that reality is stranger and more remarkable than myths imagined. The return to wonder is not a return to ignorance, but to informed amazement. When you look up at the night sky now, you see not just stars, but the product of quantum fluctuations inflated to cosmic scales, structures formed from tiny variations in the early universe, light that has travelled billions of years from galaxies racing away in an accelerating expansion driven by vacuum energy. You see a universe that arose from the quantum vacuum, a something that emerged from a nothing that was not quite nothing after all. You see the manifestation of conservation laws, the result of symmetry breaking, the consequence of fields permeating all of space. The sky is not decoration, but history, physics, and mystery combined. The return also means accepting uncertainty. Despite all we have learned, fundamental questions remain. The cosmological constant problem persists. The nature of dark matter is unknown. The mechanism that triggered inflation is unclear. Quantum gravity remains unformulated. Each answer reveals new questions, showing that understanding is progressive, never complete. It is not failure, but the natural state of science. We know more than we did, and future generations will know more than we do. The return to wonder includes accepting that mystery is not eliminated by knowledge but transformed, that some questions yield while others emerge, that the boundary of understanding is always moving but never disappears. The return also means integrating this understanding into lived experience, knowing that you are made of quantum fields, that the atoms in your body were forged in stars, that the vacuum surrounding you is not empty but structured, changes perspective. You are not separate from the universe but part of it, a temporary arrangement of matter that arose from the same quantum fluctuations that seeded galaxies. This can provide comfort or perspective. The concerns of daily life, however real and important, are brief episodes in a cosmic story extending billions of years. You are connected to that story, made of its substance, shaped by its history. This does not diminish personal meaning but embeds it in a larger context. The return to the present moment, after this exploration, brings enriched awareness. The question of whether the universe came from nothing has been explored through physics. and we have discovered that nothing in the physical sense is something, that creation is balanced, that origins are natural. The ancient question has been addressed, not completely resolved, but significantly illuminated. As you return now to rest, to the gentle rhythm of breathing, to the quiet space of approaching sleep, carry with you the understanding that the universe is both comprehensible and mysterious. Physics has shown that something can come from the quantum vacuum, that conservation permits creation, that existence is balanced. But ultimate questions remain, inviting future inquiry, guiding continued exploration. The legacy of this investigation is knowledge built through patience and rigor, wonder deepened through understanding, mystery transformed but not eliminated. The return is to see the world with new eyes, to recognize that the vacuum is not empty, that existence is remarkable, that the question of origins connects the deepest physics to the most profound human concerns. Thank you for traveling through this exploration tonight. If you found value in these reflections, if the journey helped you rest, if the questions inspired thought or calmed the mind, then perhaps you will return to wonder again, continuing to ask how and why, knowing that each answer opens new questions, and that the search itself is part of what makes existence meaningful. Sleep well beneath the stars, under the quantum vacuum that is not empty, within the universe that arose from the balance of positive and negative, part of the cosmic story that began with fluctuations and continues through you. The universe came from nothing that was something, and in understanding this, we see that existence is both explained and inexplicable, both natural and miraculous, both comprehensible and forever wonderful.